for geometric computing in CVPR 2023. Our workshop is hybrid. Thanks for everyone coming here in person. We will see half or maybe the half of our organizing committee on the Zoom there. Okay, there are still newcomers. Hello, you're not that late. Yeah, let's start. So, as machine learning methods dominate the computer vision field and now deep learning field and now generative models, public data sets, benchmarks, and evaluations have started to play an important role for relative scalability and reliability of different approaches. And driven by different communities, there are different tasks, there are different data sets for to push the limits of what we can achieve by using the same annotation data sets. However, these data sets and these advances are a little bit less about global shape understanding, parameterized decompositions, hierarchical decompositions, more about like introducing like what are the control elements or structural decompositions, etc. So this workshop focuses on geometric deep learning for shape understanding for geometric computing and brings together researchers with different perspectives by raising public data sets and baselines. And I am sure as the fifth version is going on right now, you have heard about skeleton challenges, and that is what is the public data sets and baselines mentioned here. We also want to create those global challenges to benchmark different approaches so that we will advance the field all together collaboratively. And we also want to organize a workshop to spark new collaborations, bring visibility to new ideas, and highlight the important work in the field. This is our wonderful organizing committee. Dana has taken the flag for the past couple of the RGC workshops, and she is almost single-handedly everything. We are trying to support her in everything. I'm here as one of the in-person organizers. Dana is one of the other in-person organizers. Probably Catherine everywhere in the world. We also want to thank our program committee for the incredible reviews and for helping us see the value in the papers. Then we have the challenges, as I mentioned. So Skeleton has, we will also hear about these a little bit later in the afternoon about challenges, but just to give information, we have 4 tracks in Skeleton for the different challenges. The first one is Pixar Skeleton. By the way, Skeleton comes from the fact that these were all skeleton-oriented challenges. So instead of saying like skeleton challenges, we say SkelNet because we want to do it with deep learning. So SkelNet is on. So SkelNet on. Anyway, so Skeleton looks at binary shapes and binary skeletons. Can we actually extract skeletons from silhouettes? And this is about employing existing 2D architectures for global shape understanding, and we want those approaches to be robust to overcome noise, unnecessary branching, you know, like similar to what we would expect from traditional skeleton extraction approaches. In the second one, we have skeleton. So if you think about images as like those grids which are structured, then we are going with unstructured domain by finding skeletons from point clouds. And this global shape understanding in unstructured domains are flexible. We want them to be flexible against varying noise distribution, sampling density, etc. By the way, disclaimer, I have been battling with allergies for the past 2 days, so if my voice keep degrading all the time, I'm really sorry about that. Okay. Third one, we have parametric skeleton, which is looking at chip, pixels, and parametric skeleton. So similar to the silhouette version, but can we actually extract the skeleton in a parametric way? Can we use Bezier curves for that? Main challenge here is the curve domain and embeddings because we are actually changing the domain instead of staying in the same silhouette or point cloud domain. And the last one, we have image skeleton, which is looking at complex RGB images instead of silhouettes and trying to extract binary skeletons. And sometimes we have seen more look like living creations which really have skeletons, but what we talk about are basically the shape skeletons, not just like animated living things skeletons. So let's come back to the workshop. Again, thanks for the program committee for their efforts, and double thanks for last minute reviewers. We had 3-4 reviews per paper. We got positive average rating, and here are the beautiful presentation selected papers. We will have GPRNet, geometric prototypical network for point cloud few-shot learning. Then we will have Johnson, unsupervised generic garment simulator, and then we will have improving shape awareness and interpretability in deep networks using geometric moments. Here is our workshop program. Right after I finish talking, and start with first keynote, then we have the presser session, then we will have keynote, then we will again going the same way like keynote, presentation, etc. At the end, at 6:15, we will have an open discussion and panel, and I hope everyone will be here so that we can actually spark new ideas and new projects. If we go to our workshop keynotes, sorry, we will have Roland Altaşe, senior research manager at NVIDIA and then adjunct professor at TUM. We will also have Yifan, assistant professor at National University of Singapore. Then we will have Theodore Kim, who is a lovely person and friend from Pixar at some point. Sorry, too much information. Associate professor at Yale University. And again, I wanted to mention that collaboration session, be here because that is my favorite part of the workshop at some point, that how we can collaborate together, how we can spark new ideas, what the field is going on, how we can do something that for the open challenges or what we cannot do by ourselves, but we need to get together to do. All right, so skeleton challenges are open. You can go to these links. Zoom link, I think this year is not available, so I did not put them into the slides, but website, program, everything is there. If at any point you forget about the website or link anything, just go to bit.ly/TRGC23. And everything is there. So without further ado, I would like to first announce our first keynote. I think I flew through the slides, so it may be like 5 minutes early, but maybe, I don't know, we don't take questions for opening remarks, but if there's anything that I did not mention, either like organizers wants to mention or anyone from the crowd. No? Yes? Okay, so then maybe we can start with the first keynote. I just want to flash our program one last time so that if you want to take photos or if you want to remember some talks, everything is here. Okay, I'm just trying to be Laura, are you online? I'm sorry, we are a little bit early, but if you are online, I just wanted to make sure. Okay, we can wait a couple of minutes. Oh, okay, okay. Good to say, good to know.
Then our talk is till 9:15.
Okay. That's great. So it seems our keynote is presenting right now in another workshop and her talk will end at 9:15. So that's why we are having this 2-minute break. So as soon as her other talk ends, hopefully she will be here. So sorry about the 3 minutes early opening remarks. Hello, newcomers. You are not late. We are just waiting for our keynote speaker to join our bridge. So people just coming, we are waiting for our keynote speaker to join the call, so that's why we are having a little delay. Sorry about that.
Otherwise, when the first presentation is there.
Okay, you want to switch these two?
Yeah.
Okay.
It's process session. Yeah.
Yay! Hi, Laura.
Hi.
Thanks for joining me. So let me do a quick intro. Laura Hansher is a senior research manager at NVIDIA and also an adjunct professor at the Technical University of Munich, leading the Dynamic Vision and Learning Group. From 2018 until 2022, she was a tenure track professor at TUM. Before that, she spent 2 years as a postdoctoral researcher at ETH Zurich, Switzerland, and a year as a senior postdoctoral researcher in the computer vision group at the Technical University in Munich. She obtained her PhD from Leibniz University of Hanover in Germany and spending a year as a visiting scholar at the University of Michigan Ann Arbor, USA. She is a recipient of the Sofia Kovales. I am butchering the names. I'm really sorry. Sofia Kovales Kaja Award of 1.65 million euros in 2027, the Google Faculty Award in 2021, and the prestigious ERC Starting Grant in 2022. Today, she will talk about multiple object tracking with graphs from classical to light. And without further ado, thanks for joining us, and the stage is yours.
Thank you. Thank you for the kind introduction. Sorry I'm late. I was just finishing a talk at another workshop. May I actually share the screen? It says I don't have permission. Okay. Does it work properly?
Yeah, just give us 1 second to put you on the big screen. Yeah, you're ready to go.
Okay, awesome. Perfect. So yeah, thank you for the invitation, first of all. So today I want to talk a little bit about how graphs and how graph neural networks in particular can help us for multiple object tracking, and why using graph neural networks is the natural thing to do to solve this problem. So I'm going to start with a little bit of an introduction, since I know the crowd is not only multiple object tracking fans. So the multiple object tracking problem is the one where you have a series of frames in your video, and given this video, you want to find out which parts of the image depict the same object in different frames, right? So you want to end up obtaining trajectories that look like this. They could be represented by bounding boxes, they could be represented by segmentation masks, but at the end of the day, the hard problem is to actually connect these boxes across time so that they depict a coherent trajectory. Now, one might ask, well, why do we actually need tracking, right? So the first question, and especially coming from detection people, is why do we need tracking when we have detection, right? So it turns out that at some point, detection is going to fail, right? So one mode of failing is an obvious one where the object is actually occluded. But there are also other failure modes, which include viewpoint variations, pose variations, blurring, illumination variations, that actually allow to detect the object only in a few frames of the video. And you can have also, for example, background clutter, right? But at the same time, one needs to perform tracking, and especially multi-object tracking, because we want to understand and reason about the dynamic world, right? We want, for example, to be able to predict the trajectory of a person that is crossing the street in case of an autonomous car, for example. And for this, we need to properly understand the past trajectory, which means that we need to perform object tracking. Now, in the literature and in the community, tracking has been posed as many things, right? It has been posed as measuring similarity, as correlation, as correspondence, like most problems actually in computer vision, also as a matching problem or a retrieval problem. But today I'm going to use mostly the formulation of data association. Now, tracking is also, for example, learning to model our target, learning about the appearance of our target, how our target looks like. And for this, there are sort of subfields and subcommunities that have been working on single object tracking or on re-identification, which focuses heavily on appearance. And the second thing we need to learn to model our target is motion, right? We need to make predictions of where the target goes. We need to learn how it moves. And for this, the community of trajectory prediction is actually very strong in learning motion, in learning interactions between objects. But let me go back to that formulation of data association. Why do I pose tracking as a data association problem? Well, this comes from using the paradigm of tracking by detection. So tracking is such a huge problem that we tend to break it down in two parts. We tend to use detections as input, right? So these are our proposals, if you will. And then what we have to do is we have to associate these detections in time in order to obtain full trajectories. So you see here that I've represented trajectories as just color-coded bounding boxes. So if two bounding boxes have the same color, it means that they represent the same person, the same trajectory. And so association, for this talk, I want to kind of break it down into two types of association. One is short-term association, which is the frame-by-frame association. And this is usually done with, tracking by regression or tracking by attention. So methods that essentially predict what is going to be the position of the object in the next frame. So it performs this short-term association from frame to frame. And this is usually the case for online trackers. Now, of course, they are very fast they are very good for real-time applications, but they usually lack robustness under occlusions. And for this, people have worked also on what we call long-term association. So what happens when I actually want to fill the gap of, for example, this blue trajectory, where we have this frame in which the person appears, then all the other frames in which we have no evidence that the person is there, and suddenly it reappears here a number of frames later. I need to connect these two detections. I need to perform data association, but this is not really short-term data association. And for this, I have to come up with different methods. There are the ones that are used in long-term association. Now, one type of long-term association that has been used already since, I think it was something like 2007, when it was introduced, this formulation, is graph-based association. So what I'm going to do is I'm going to pose the tracking problem as a graphical model, where the nodes are going to represent my detections and the edges are going to represent possible trajectories. So in this formulation, a trajectory across the video, for example, this red trajectory, is going to be represented by a series of connections, a series of edges that are going to tell me that these two red detections are actually connected. They actually belong to the same trajectory. And so I'm going to do the same with all the objects in this video. And in the end, what I'm going to obtain is these three trajectories across the graph that represent the three trajectories of the objects in the video. And so just as a little bit of a vocabulary, because I'm going to use this interchangeably, before deep learning, we used to solve this with classic optimization. And so we used to work with network flows. This is where this word flow comes in. So a node represents a detection, an edge represents a trajectory, also represents a flow in this vocabulary of the optimization that we're going to use. And in this case, one unit of flow is going to represent one pedestrian. So let's see what this unit of flow really means. So in order to find the trajectories in this graph, we're going to solve what is called the minimum cost flow problem, which essentially means determining the minimum cost of shipment of a commodity through a network. Now, in our case, the commodity are the pedestrians, right? So one unit of flow means one pedestrian, and we want to find the minimum cost of shipment, which means the optimal route to send this pedestrian from the beginning of the video towards the end of the video, right? What is the optimal path for the pedestrian to follow through this graph? And of course, the cool thing about this is that I'm going to find the solution for all three pedestrians at the same time. So it's not like every pedestrian can choose the path independently, but I'm actually going to find a solution that satisfies all three pedestrians. So I can send all pedestrians from the beginning to the end of the video. Now, of course, this is an optimization problem. So we're going to be driven by the objective function, which is a minimization function. And actually, what is going to drive the tracking is this term Cij, which is the cost that I'm going to assign to an edge. So how do I actually define this cost? So remember that we have in front of us a minimization problem, which means that if two detections belong to the same person, I want the edge between these two detections to be active. I want this trajectory to be created. And so since this is a minimization problem, I'm going to assign a very, very low cost to the edge connecting these two detections. So low cost is good for a minimization problem. It means that it's probably going to be used in the final solution. What happens when I have two detections that don't belong to the same trajectory? I'm going to want to assign a very high cost to the edge connecting these two detections, indicating the objective function that I don't really want this edge to be part of my solution. Now, the other things that one needs to know is that we have an indicator function, which is going to become very useful later, in which if an edge is active, So if it's connecting two detections and creating a trajectory, I'm going to assign 1 to this indicator function. If an edge is not active, I'm going to assign 0. And this is how I obtain the optimal set of trajectories. Now, everything that I've presented so far is a pipeline for graph-based association in which we extract detections, we compute some usually handcrafted features, and we assign them to costs in the edges. And then we run our optimization problem to obtain the trajectories. There is absolutely no machine learning involved in this pipeline. So as you can imagine, there's a lot that we can do in this space to improve things and to try to learn more and more from data. So the first thing that one can do very obviously is actually to learn the cost, right? Why should I handcraft the cost that I'm going to assign to an edge? I'm just going to take two detections. I'm going to put some geometric cues in there, and I'm going to let a neural network decide what cost should I put on that edge that connects these two detections. Now, one hopes that if these two detections don't represent the same trajectory, the cost is going to be very high, while if the two detections actually represent the same trajectory, the neural network assigns a very low cost. And this is basically the loss function that I'm going to use to train this neural network. So this is cool, right? We obtain more robust trackers, etc. But I still don't like that we have this feature extraction, which is now learned, and we have this optimization, which happens after it. This is actually not learned, and it's actually completely independent from the feature extraction. So the bad thing about this method is that we're not really learning the features in the right domain, right? So the domain for optimization is the graph domain, but the way that I learn my features is not taking into account this graph domain. So this doesn't sound right. And there's so much more that we can do, maybe unsurprisingly, using graph neural networks, right? So now that we know how to cast the mode problem into a graph, we can use graph neural networks in order to learn features directly in the mode domain. So here I'm representing, as always, my input detections and the graph that I've created with these input detections. And now what I need to do in order to use graph neural networks is to define some embeddings, right? To define node embeddings, which are simply a tiny CNN that takes in the input image, the input detection, and computes a feature embedding from that. And the edge embeddings. These are slightly more complicated, and we do have a tiny bit of handcrafting in there that we're improving in subsequent papers. But essentially what we want to encode in these edges is a ton of geometric information. So relative box position, relative box size, the time distance between detections, and also some appearance in there. And by appearance, I mean the difference of appearance between the two nodes that the edge is connecting. Some kind of re-identification, if you will. So now I have my initial embeddings, the node embeddings and the edge embeddings. And now what I can do is I can let the magic happen, right? So we use message passing networks, which essentially propagate these node and edge embeddings all over the graph, right? So what these methods do is essentially they have a series of message passing steps in which nodes communicate with edges and edges communicate with nodes. So you can imagine that after n message passing steps, if I'm a node that before any message passing, I was only aware of the own appearance of the detection that I represent. Now, after n message passing steps, I have a view of my neighbors. I have a view of what kind of other detections are out there. Is there, for example, a detection that is 5 frames away that looks exactly like me? This is now an information that I can have thanks to these message passings. And so this is really cool, right? Because now my embeddings, my node embeddings and my edge embeddings are going to be updated, but they're going to be updated exactly with the information I need for tracking, which is sort of a higher level information about what is happening in the neighborhood of the node. And so after this series of message passing steps, which are of course learned, now the only thing I need to do is basically solve a classification problem, right? Is this edge active or not? And this is what's going to give me directly the trajectories. So essentially my loss is going to be a classification loss. Is this edge active or not? But of course, like before I did this neural message passing, an edge, in order to say, am I active or not, it only had the information of the nodes that it connected. So it could say, you know, do these nodes look similar? Do these two detections look similar? Sure, you can have some kind of appearance information. Are these bounding boxes far away from each other, for example, for some position information? But after a series of message passing steps, I have now a much broader view of the problem, right? If I'm connected to this node, are 3, 4, 5 nodes in the future, am I still going to have connections that have, for example, a similar appearance? So is there going to be continuity to this track, right? Imagine like the power of this for tracking, right? This is exactly why we want to have this formulation and why message passing is so powerful for multi-object tracking. And so after classifying these edges, I obtain my trajectories and my job is done. So this is all great, right? And what I particularly like about this formulation is that now instead of having, separate feature extraction and learnable and data association, since now the data association is learnable, I can actually backpropagate through the whole thing. So I'm actually extracting features that are good for the mod domain, which is in this case expressed with a graph. Now, I'm only going to show this one result because I really like this. It really shows the power of message passing for tracking. So in the x-axis, we have plotted the number of message passing steps. And in the y-axis, we have plotted two accuracies. On the left, MOTA, and on the right, IDF1. These are two metrics that we commonly use in tracking. And we see here the jump in performance that we have when we go from 0 message passing steps to 2, right? So this is only an update step from nodes to edges and from edges to nodes, right? So the only thing that we did is that I as a node have talked to my neighboring nodes and I've seen what is around, do they look the same appearance-wise? Are they close to me distance-wise, etc.? This exchange and collection of higher order information from neighboring nodes makes a huge difference for accuracy in tracking. And you see that after that, you still keep improving things, but this first step of collecting information is when things really happen. So I think this is really cool and really motivates the use of message passing networks for tracking. Cool. So I've started this talk by saying we want to use this for long-term association, right? And I can say, sure, you can take 25 frames, create a graph, solve the graph, and we have solved these occlusions of up to 25 frames. And you're like, look, Laura, this is not really long-term association, right? I'm talking about 100 frames, 500 frames, 1,000 frames, the whole sequence. And then I say, whoa, this is a huge graph, especially if you start connecting everyone with everyone. If you start, even if you do some edge pruning, you're still going to have a huge graph that it's going to be hard to fit into memory. But most importantly, you're going to have a huge problem of imbalance between active and inactive edges. This means that you're going to have a lot of edges that are going to have to be labeled as inactive and just a few that are going to be labeled as active. And we know what happens when we have these kind of imbalances, right? The active edges don't have any effect on the loss, and it's really, really hard to learn in these conditions. So how can we actually make this scalable to 500, 700, 1,000 frames? Well, we look back at the literature and we said, hey, most of the trackers are actually hybrid, right? So they have some sort of short-term processing, tracking frame by frame. And then they also have, in parallel, another type of processing for long-term occlusions, right? And you usually don't really write this down, right? You find it somewhere hidden in implementation details where it's written, oh yeah, we use a re-identification model to solve long occlusions, done. And it turns out that when we analyze the literature, we found that actually all trackers are hybrid multi-level trackers. But each of these processing, short-term, long-term, even mid-term sometimes, they are different, right? So every processing is engineered per level, right? There's a type of tracking for short-term, another type for long-term, different hyperparameters, completely crazy and completely non-scalable. So what we actually want to have is a unified hierarchical tracker where each tracker, short-term, mid-term, long-term, is the exact same tracker, so that it's highly scalable and it's unified and not really engineered for each particular level. Now, what do I mean by a hierarchical tracker? I mean a tracker that takes 5 frames as input. It finds the tracklets for these 5 frames. And then you go to this next level and you find tracklets for 25 frames. And you go to the next level and you find tracklets for 75 frames. And you keep growing and growing and growing until you reach the whole sequence, if you will. So this is essentially what we propose, a delicious and yet very strong tracker, which we name Sushi, for a strong, unified, scalable, hierarchical multi-object tracker, which essentially is going to take our input frames and it's going to create trajectories in a hierarchical way. Now, the cool thing is that we can now process really long clips, which is something that one cannot do with a monolithic graph, as I've explained before. So now we can process long clips of 500 frames. We can solve occlusions up to 500 frames. And we have the exact same graph neural network architecture and weights for each level. So really a general tracker, we don't need to engineer each level. And also the cool thing is that it generalizes, right? So as much as I love mod challenge and working on mod challenge for obvious reasons, we also want to generalize to other data sets out there. And so we tried on 4 diverse data sets and we have consistent state-of-the-art results by a large margin. Now, as I've said briefly, how this works is by creating tracklets which are increasingly long in time. So we have the first Sushi block, which is essentially the graph neural network that I've explained, which takes detections, it expresses them as nodes, and then solves the problem to obtain trajectories. Now, at the second level, things need to change a little bit, right? Because your nodes no longer represent detections, but they represent tracklets. Now they represent tracklets, which are the solution coming from the previous Sushi block. And so now your node is going to represent a tracklet, but you're still going to have the exact same graph neural network that is going to solve the problem and connect these tracklets into even longer tracklets. And you do this for several levels until you obtain full trajectories. Now, as I've said, one of the cool things is that we're not going to have 9 Sushi blocks, each with their own weights and, have this huge model, but we're going to have exactly the same architecture, exactly the same weights that are shared at each hierarchical level. And so what is cool here is that we have a model that is not really huge, but that at each level is going to learn which features to use, right? So intuitively, when I think about it, if I think about short-term association, I'm going to look more at position, right? So objects don't just fly from one part of the image to the other, but they move rather slowly from frame to frame. So position is a very strong indicator for short-term association. For long-term association, on the other hand, the object has been occluded for a while. It could be anywhere, right? Position is not a strong cue, which is why we usually rely on appearance, right? We rely on re-identification. And so the GNN, what it's going to do is at each level, it's going to choose which features to use. right? Depending on what works best at each hierarchy level. And this is not something that we have to choose, but actually the model can choose on its own. So again, a little bit of an overview of the pipeline. We have our detections as input, right? So this is still a tracking by detection method. We have our sushi block, which acts at the first level on just 5 frames. And from these 5 frames, we obtain the trajectories. Now, once we have these trajectories from frame 1 to 5, from frame 6 to 10, from frame 11 to 15, what we have now is another sushi block that takes these 3 outputs and tries to connect these tracklets among themselves to see how many trajectories can we get from frame 0 to frame 15. And we do this in a hierarchical way, right? Slowly for 5, 25 frames, 50, 150, we keep growing and growing and growing until we reach 1,000 frames or how many frames you need. Now, let's look at some ablation studies to see, like all this hierarchy, like how important is it, right? So I really like this experiment because it clearly shows how powerful it is to have such a hierarchy in tracking and especially in graph neural networks. And so here what we're going to plot is in the x-axis, we're going to have the hierarchy levels. So one hierarchy level is essentially a monolithic graph that takes in the whole input and solve for the trajectories, and that's it. 3 levels is going to be, for example, 5, 25, and 512. And you go all the way up to 9 levels. And here on the y-axis, we're going to have the clip size that we're going to work with. So clip size of 8 means that I'm only going to be able to solve occlusions up to 8 frames. Anything else, I cannot solve for these occlusions. Of course, what we want to reach is something like 512, for example, which means taking in the full sequence in, so that if a person appears in the first frame, then it's occluded for the whole video and then reappears in the last frame. I want to have an edge connecting these 2 detections. I want to have the possibility of connecting these 2 detections if indeed it's the same trajectory. So with one hierarchy level, first of all, the first thing that we see is that it doesn't fit into memory to create a graph with one hierarchy level that connects the detections at frame 1 to the detections at frame 512. Even if you do edge pruning, it doesn't fit. But even if it would fit, learning in these conditions is really hard. So you see how we obtain this IDF1 accuracy for clips of 8, pretty much the same for clips of 32, but things start to get worse as we increase the clip size. And this is because of the imbalance problem that I told you about before. There are so many edges that should be labeled as inactive that it's really hard to learn about those few active edges, right? So the training signal there is just too small. And we try to have solutions in the loss function to balance that, but it's still too much of an imbalance problem. Now, what happens when we go to hierarchy level 3? First of all, we see an increase in performance across levels. So in general, it just works better for the same clip size. But the most interesting thing is that the performance keeps increasing as we increase the clip size, which was not the case for the monolithic graphs. So now we have a solution where we actually improve results as we increase the clip size, which is what we would hope, right? If we have a larger clip size, we can solve for larger occlusions, we should have better IDF1 performance. And indeed, we see that the top performance happens for clip size 512 and 9 hierarchy levels. So this is actually 13 points in IDF1, right? 13 points that we have gained from going from monolithic graphs all the way to this hierarchy of 9 graphs. So I think this is really a huge boost in performance. Now, let's see some qualitative results just to understand what is happening here. So at the level 1, as I've said here, we're dealing with maybe 5 frames, and we're finding tracklets in these 5 frames. which means that every 5 frames, our identity is going to change because the first 5 frames and the second 5 frames are not really connected, right? These are 2 different graphs that have been solved. So you see all the colors here flickering because these identities are changing every 5 frames. At level 3, we can see some more consistency, right? So tracklets get longer and longer, 25 frames, right? Things are pretty much stable when we go to level 6 or very, very stable at level 9, where we can really obtain these very, very long trajectories, and we can even fill gaps across 500 frames. So as far as datasets go, as I've said, we don't want to focus only on mod challenge, right? So we work on mod 17, which is kind of the standard dataset of mod challenge. We also work on mod 20, which is this crazy dataset in which we have more than 100 objects per scene. So you see here the level of crowdness that we're working in. And this is, of course, also a problem for graph trackers, right? Because we need to create a graph that contains all these people, right? Each detection is going to be a node for us. And so it is also a problem memory-wise. And so what's going to happen is that for monolithic graphs, we can only solve occlusions up to maybe 20, 25 frames, right? Which is very, very limited. So this shows another powerful benefit of having hierarchical tracking. And then we also tried another datasets, like, for example, DenseTrack that contains more abrupt motion, or BDD that contains car tracking, so that we have completely different features and we still show that our method generalizes. Now for some benchmark results. So I think a cool thing here is that we are improving results not by a little bit, but by a really large margin, which shows 2 things. First of all, of course, that the formulation is very powerful, but also that there are really long occlusions that nobody has really targeted before, right? On some data sets, we have an increase of almost 10 points in IDF1. This is a huge, huge improvement and shows really that there were many occlusions that people were not even trying to solve because they are really long occlusions, and it's really hard to connect these dots without creating false trajectories, without creating a lot of trajectories that are not really there. And as you can see, the improvement happens all across the board. Okay, so I want to leave quite some time for discussion. So what I've presented and hopefully convince you of is that graph neural networks are actually really powerful and robust trackers. They are capable of adapting to short and long-term association challenges, which is perfect because now we don't need to engineer every bit and piece and put some features for short tracking, then some features for midterm tracking, and some others for long-term tracking. We just put everything in there, and the neural network is going to learn which features to use at each time. And in case you were wondering if you can do 3D tracking, if you can do online tracking, the answer is yes. And we had a paper that was presented last year, which is called Polar Mod, that explains exactly how to use this kind of graph neural network formulation and use it for LiDAR tracking. And the cool thing about that is that we use only geometric relations. We didn't use any type of appearance. And we show that the tracker is so robust because of this graph formulation that we obtain state-of-the-art and we actually generalize to other data sets. We generalize across LiDAR sensors, we generalize across locations, because we use only this geometric information and a really robust graph structure for tracking. And the other cool thing about Polar Mod is that it's actually online. So we show how this tracker that I've presented right now, which is basically an offline tracker, right? So it takes the 1000 frames, it solves the trajectory, and it gives you the trajectory for all 1000 frames, right? So it's not really online. While if you want to have an online tracker where as soon as a frame comes in, you process it and you obtain the position of the tracks in this new frame, and you keep going as soon as the frame comes in. You can still do this with graph neural networks, right? And we show in that paper how to adapt the tracker in order to make it work online. So if you're interested, also check it out. Now, I do want to say that this paper, the sushi paper, is going to be presented at CVPR. I have omitted many of the details, but if you're interested, go check it out. Go talk to Orchon and Guillem, who are both authors that are going to be present here at the conference. So with this, thank you very much for your attention, and I'll be happy to answer any questions you have.
Thank you, Laura. Maybe we can start with one questions because some questions
So I have to say that I don't hear you really well when you talk.
Okay. There are some questions from the chat, so let's first look at that. Sorry.
So the question is, how do you obtain or generate the training data or the intros? You can
Right.
put in the chat if you don't understand us, and I will try to fix that.
Yes. So, okay, the question is, how do you obtain or generate the training data or ground truth? So for my challenge, this was a fun postdoc time that I had where I was labeling manually a lot of sequences, and I'm not joking here. So of course, there's a lot of manual work in labeling these sequences, and most of the sequences that we work with are manually labeled. Now, a cool thing that we're starting to do now is we're starting to use offline trackers, right? So trackers that are more robust, like the one that I've presented, to label sequences to train online trackers, right? And I think this is really cool because there are just maybe a few cases that offline trackers cannot really resolve nowadays. And these are the ones that you can actually tell an annotator to solve. So this is something that we're working on, trying to use this for auto-labeling, trying to improve the labeling pipeline so that, someone doesn't need to spend their postdoc time labeling more challenge sequences. I can go on and read the questions from the chat.
Yes, that sounds good.
Okay, awesome. So someone says that sushi depends on detection results to work. Are you considering integrating detection as part of the pipeline to make the whole solution end-to-end? This is actually a great question. So for now, sushi is a tracking by detection method, which indeed it means that the tracking step and the detection step are completely independent. So we are thinking into how to integrate detection as part of the pipeline. But of course, you need to create the graph from something, right? So you could create the graph, for example, from proposals instead of detection. So then you would have more nodes and you would need to decide between, for example, 5 proposals that represent one object, which one shall I choose? So it's not only one detection per object anymore. So it's a bit of a different formulation. But so far, we haven't found a way of doing this end-to-end. So in order to work in an end-to-end fashion, I would recommend checking, for example, our tracker TrackFormer, which is based on transformers, which are essentially graph neural networks, right? And there indeed you have the detection and the tracking step completely coupled, right? So for each frame of the video, it's going to tell you where the objects are, whether these are new objects or these are already tracked objects. And there's a transformer that it's going to do this frame by frame. So this is an online tracker. So that's also a really powerful tracker. I have to say it requires a lot more data to be trained. So as anything with transformers, a lot of data helps. Otherwise, results are really not the best. So of course, there are pros and cons, right? But this is, I think, the closest that you can get to a real tight integration between detection and tracking. Okay, then there's another question by Kevin that says, have you tried this with distant or small objects? For example, 5 or 20 pixels per detection. I don't think we have those type of objects in Mod Challenge. I think the threshold for the objects is actually larger, for which we just cut objects and do not evaluate that. I could imagine that if we do have a detector that works for that size, then graph should be a good option for that. Even if, for example, the appearance information would be bad because there's not much appearance that you can get with 5 pixels. We showed in Polar Mod that we can use only geometry information for tracking. And the actual formulation is very robust because you have this graph that solves for all the tracks at the same time. And so it could also work for these small objects. The question is more if there's any data set that has them annotated, but I imagine that it would work, yes. Okay, there's another question. Should I just go on, or is there a question from the audience? So I cannot really hear anything from the microphone. It's all garbled. Okay, so the sound problems, you will try to fix that in the break. Okay. So I'm just gonna read the third question from the chat. So it says about the 3D case, what is the form of the data? Voxels, 3D points, meshes, or another form? So in our case, we use 3D points. So we use the LiDAR output, and then we have a detector on top, a 3D detector. And after that, it's exactly the same as sushi, or in our case, we use monolithic graphs still in that work. But once you have the detections, then it's really the same formulation. So it really depends on the tracker. Okay, so a question from the audience, I assume, can these graphs be used for multitask objective for long-term video understanding? Ooh, that's a great question. I think so. So my goal would be to represent any task in dynamic scene understanding with graphs, right? So we have seen like scene graphs, like there's a lot of work on scene graphs. There's work on representing interactions between objects with graphs, right? So I think it's really a great representation to just distill in general interactions between dynamic objects from, you know, one frame to the next, which is the case of tracking, from dynamic to static objects, which is more the case of scene graphs. So I think that one could have any type of task that is just represented by a huge graph that represents all the interactions, and then you train it with whatever objective you want, right? So I think this would be kind of a really cool work to perform dynamic scene understanding in the general level, which is what we're going for with tracking, right?
Thank you. Another question from the room? If not, we can go to the poster session, which I think we have one poster there. So let's type my button. Thank you, and we will be calling next 10:45. Presentation collection. Working with like 10% range.
We anyway only have 20, right?
Huh?
We anyway only have 20, so 10 is half of it. Um,
Hi.
Hi, Bernard. Can you just tell us how well you hear us? Can you hear us now?
So now it's a bit better, but it was just completely impossible to hear
Yeah.
any single word.
Can you hear this? Hello, hello, hello? Can
I
you
think
hear
the other microphone works better. Yeah.
this one? Can you hear this?
Yep.
Yes.
Yep.
Yeah.
So this is that.
Yeah.
Yes.
Okay.
Is there a way to like just not even include this?
Test.
Can you hear this? Hello?
Yeah, we can
Uh,
hear you, but it's garbled.
Is it
It's not,
clear now?
Yeah.
it's a little bit better, but it's still very garbled.
Yeah,
Is
but
this
I think
better?
maybe if you say just one word, we can just hear that you ask, can you
Hello?
hear me? But when Ilke was talking, it was almost impossible to hear
And
it.
when we are talking now, you can hear it clearly or not? No?
Now it's fine. I think it's also a distance issue. If you
Yeah,
stand a
maybe.
little bit back, it's better. If you stand closer, it's bad.
So this is okay?
No,
No.
yeah, exactly.
Oh, so stay further.
Yeah,
Yeah, I
Wow.
think it's closer you are, it saturates and clips.
yeah,
So-
exactly.
I was
Yeah.
getting closer and closer because you didn't hear.
Yeah, then it gets worse and worse.
Yeah,
If
that
you
was
just talk like this, everything is fine?
Yes, yes.
Okay.
Yeah.
Okay.
Good. Let's do that then. Zoom should clip it, however. Yeah, okay. We will tell that the speaker who will present in person. And we should put the
Oh, yeah.
what is it? 9:45?
10:45.
What's that like? Are you? In the West building, have you been in the West building where you picked up the badge? There is behind the things where you pick up the badge, there is a huge staircase that goes down. So you have to go into the cellar basically, and there is one poster room where all the posters of all the workshops are located.
Thank you.
Yes. Okay, and then I will also prepare the video.
Do you want to check the videos of the audio for the videos? Because once also we had a problem when we shared the audio.
I'm just trying that.
Okay.
And it seems to not work.
It is an unsupervised generic neural government simulator. Thanks for joining our presentation of CVPR net geometry. It is prototypical network for pointers in geometry and based on data analysis of laboratory movement after it.
Did you hear that?
Use data sets like
It was very low.
process require data-driven deep learning to
generalize on them.
Is that better?
Okay, now
Networks
it's
like
better, yeah.
Net
Perfect.
and Vision Transformers VIT perform really well on these huge
Can you
data
hear
sets
it when
with
I
large
mute
number
myself?
of model parameters. We ask a question, can these deep learning models also learn and generalize well on few samples?
That's perfect now.
Yeah, but the
These deep learning models usually
lot of
come
quality
with
issues in the
limitations. They are often data driven and require large amount of training data to generalize. Also, they are
Did you have quality issues in the video, like the visual quality?
And when I muted myself, it kept going.
Yeah, but I'm saying the visual quality was bad. I don't know how it was.
Yeah,
for
the video, I think, probably it was not loaded completely, or at the top there was just some issues.
yeah.
Okay.
they could be offering due to which
meta learning is also not possible. Enrich features for few-shot point cloud classification. Propose an embedding network to train supervised classification task for the training and then do a few-shot evaluation. Although this method performs really well on ModelNet 40 but comes with many caveats due to data-driven supervised training causing distribution drift to novel tasks. In
I think the first few seconds it just happened. I don't know if you can see also the thing
Yeah,
in the
I think it's the
visualization.
zoom controls.
Yeah,
Bernard, you might want to move the zoom controls away.
Can you tell me what the issue is? I don't know what.
can
is
you?
not-
So it's just like half of the video is just blocked with something.
It's the zoom controls.
For a short moment, right? But it was showing the whole thing for most of the time.
Yeah.
Yeah,
Yeah,
just
that was the
probably
zoom
it's just the
control.
first few seconds. It's just happened.
But for most of the time you saw it properly because one moment there was a zoom control half over it.
Yeah,
Yeah,
Got it.
okay, good. And you could hear the audio all the time.
yeah, the
Yes.
audio was fine, yeah.
Yeah, then we should be good.
Yeah.
And you will, and when we started afterwards, you just complain via the chat. We are monitoring that.
I
Yes.
couldn't hear you.
I think you have to move back a little bit.
Yeah, go back.
Data science, like, 14 million pages, 1,000 classes.
Bernard,
Yeah,
we couldn't hear what you said last time.
yeah, it was not important.
Okay, good.
Thanks for joining our presentation on GPRNet, Geometric Prototypical Network for Point Cloud.
Okay, welcome back. I hope you had a great break, found the coffee and the snacks. For all the virtual participants, can you hear us? Can you put up your hand if you can hear us or something? Say hi. Hello.
Yeah, we can hear you.
Perfect. Thank you. So for all the virtual participants, we would also like to quickly share how the weather looks in Vancouver. So that's what you're missing out. It's pouring, it's really disgusting, but it was very nice yesterday and the forecast looks great for the week. So we have our first paper presentation for today. And I will have to redo the screen sharing for that. The virtual participants should now see a static site with the first page of the presentation. The presentation is from Tejas Amika from the University of Plymouth. It's pre-recorded, but I think both of the authors are doing the Zoom meeting for questions afterwards. So I will start the presentation, and for the Zoom people, please complain if you can't hear anything.
Thanks for joining our presentation on GPRNet, Geometric Prototypical Network for Point Cloud Few-Shot Learning. I'm Tejas Anvikar, and this is a collaborative work with Dr. Dana Bazazian. Huge datasets like ImageNet with almost 14 million images of 1,000 classes require data-driven deep learning to generalize on them. Networks like ResNet and Vision Transformers VIT perform really well on these huge datasets with large number of model parameters. We ask a question, can these deep learning models also learn and generalize well on few samples? These deep learning models usually come with limitations. They are often data driven and require large amount of training data to generalize. Also, they aren't easily adaptable to new tasks. Unlike humans who are very flexible to even a single example to classify or categorize concepts. Let's take example where all these images have to be classified into whether it belongs to an aircraft or no with looking at only the highlighted images. Few-shot learning and meta learning aim to create such concrete deep learning models which are more human-like. Let's define few-shot and meta learning. Few-shot learning learns new concepts from few examples and leverages knowledge obtained from previously seen concepts, whereas meta learning learns how to learn, similar way how metadata works, where the data describes the data itself, and this accelerates the learning new tasks by leveraging previous experiences. Few-shot learning is really good evaluation protocol for meta-learning approaches, and meta-learning is a very useful method to achieve few-shot learning. Let's look at a roadmap on few-shot learning from 2015 Siamese network to 2022 GPT-3. This work focuses on metric learning approaches. We train feature extraction to contrast, that is, map similar examples close to each other and dissimilar ones away from each other in the latent space. The first pioneer work to do such was Siamese network, which was used for facial recognition task. Metric learning based meta learning is similar to the metric learning, where the feature extraction is trained to contrast, but the only change here is that we do it for episodes of data. What is episode of data? Let's take a simple example. For few-shot learning, you need to have a support set and a query set, where support set is utilized by the model to learn the priors, and these priors are used to predict on the query set. In naive or traditional few-shot learning algorithms, the training data doesn't have this strategy. Only testing is done for the novel class with the support and query strategy. But here in meta-learning, the training data is also divided into chunks of such support and query sets. Each epoch can have such multiple sets, and each set is called as an episode. The pioneering work that introduced such training strategies were matching network and prototypical networks. This work focuses on prototypical networks. Prototypical networks are simple and efficient. They use support set to estimate the prototypes for each class K by averaging the embedding of support data. Now for any given query, the class predictions are made by simply computing Euclidean distance with respect to prototypes. These distances are later used as a logit to compute cross entropy loss, and this is how the network is optimized as shown in this algorithm. Despite its performance on 2D data like Omniglot, the full potential of prototypical networks is not used in recent work on 3D domain on point clouds or meshes. The binary work to perform few-shot learning on point cloud data was self-supervised few-shot learning on point clouds by Charu Sharma. SSFSL introduces a very unique pretext task of dividing the point cloud into its cover tree. Basically, cover tree divides the point cloud into a hierarchical decomposition. Cover tree is a space partitioning algorithm where the root node or the ith level, 0th level, always has only one ball covering the entire point cloud. The higher the hierarchy you go, you fit 2 raised to I balls, and the ball size goes on decreasing smaller and smaller. They propose a self-supervised network with two heads, one classification and the other regression. The classification head tries to predict what quadrant does a given point belong in the ball, both inter and intra hierarchy of the cover tree, whereas the regression head tries to predict the distance between centroid of the ball and the queried point. Although it performs really well on point cloud few-shot learning, but it comes with many lacunas. It requires large amount of data to train the self-supervision task, and the pretext task itself is inefficient because cover tree cannot be implemented for the online training. It has to be done offline, due to which meta-learning is also not possible. Enrich features for few-shot point cloud classification. Propose an embedding network to train supervised classification task for the training and then do a few-shot evaluation. Although this method performs really well on ModelNet 40 but comes with many caveats due to data-driven supervised training causing distribution drift to novel tasks, inefficient pretext task as it is supervisedly trained, generalizing it to a novel task becomes tedious. Also, meta-learning is not possible due to attention module present in their feature extraction module, FEM. cascade graph neural networks for few-shot learning on point clouds. Propose to learn few-shot classification tasks on point cloud by using two modules, intra-object feature extraction and inter-object relation reasoning using GNNs. Despite their performance on ModelNet 40, both on meta task and few-shot learning tasks, they come with caveats because data-driven supervised training causes distribution drift, and with increase in point size and number of ways the few-shot learning has to be done, the model parameter skyrockets due to use of GCNNs or GNNs. Also, due to these reasons, meta-learning is challenging. To address the aforementioned challenges, we propose intrinsic geometry interpreters that are simply pi set of features, points, h1, h2, normal vector and the standard deviation vector. We compute h by simply taking difference between the first two nearest neighbor of the queried point. Later these two edges are used to compute the normal by simply taking cross product. Now we simply take standard deviation for all the queried points in the KNN, which gives us the standard deviation vector. Also, we propose Laplace vectors, which are simply a vector pointing towards the mean of the queried KNN group. This is widely used Laplace operator in mesh smoothing operation. Inspired from this, we simply concatenate this mesh smoothing operator with its original position vector pi to give us Laplace vectors. Here you can observe Laplace vectors with KNN k equal to 20 and KNN k equal to 40 gives a very different receptive field as it captures high frequency data with more k. Combining IGI features and Laplace vectors, we get IGI++. Our proposed IGI features act as geometric prior for point cloud few-shot classification tasks. As you can see in the highlighted regions, IGI++ features show a high response to edges and corners of the point cloud data. To perform few-shot classification task on point cloud, we pass IGI++ features to a symmetric operator like sum or mean to get permutation invariant support and query embedding. These embeddings are passed through a prototypical network. In our case, it's just a single MLP to predict labels on query set similar to ProtoNet paper. We do a simple change in this by replacing the naive Euclidean distance to hyperbolic distance, where the highlighted k is negative hyperbolic curvature. We advocate to do this transition from Euclidean space to hyperbolic space for the main reason that, as you can see in the highlighted region, the Euclidean space produces a very uniform distribution of 5-way logits which can create ambiguity while classifying, whereas the Poincare produces a very sharp distribution which handles the distribution drift. All combined makes geometric prototypical network. Due to the fact that the learning is happened purely based on geometric priors, there is no pretext task and meta training is possible. Our model is lightweight because we use just a single MLP for the prototypical network. Our model handles the distribution drift because we advocate to use hyperbolic metric learning instead of Euclidean in the prototypical network. For our benchmarking, we consider Princeton's ModelNet 40 with 40 classes of point cloud data. We uniformly sample 1024 and 512 points for our benchmarking. Unlike other approaches, we randomly sample 24 categories for meta training, and the remaining 16 categories are used for meta validation and meta testing. This ensures true robustness to novel tasks, as for every experiment we get a random permutation of class categories. We train only one multi-layer perceptron as our prototypical network. We train 4 episodic few-shot training for 50 epochs and simultaneously validate for 300 episodes of few-shot validation. For testing, we evaluate for 500 episodic few-shot testing and report 95% confidence interval for better reproducibility. We demonstrate our results on few-shot classification for 5-way 10-shot tasks. We demonstrate UMAP projections of both Euclidean and hyperbolic embedding. We can observe that the interclass distance for label prediction in Euclidean space is too low, causing distribution drift, and for Poincare or hyperbolic space, the challenge of interclass ambiguity is simply addressed by pushing the features towards the boundary of Poincare ball, which is the unique property of hyperbolic space with negative curvature. We perform ablation on few-shot classification for 5-way 10-shot tasks to prove the significance of proposed Laplace vector. Graph shows accuracy versus point density varying from 128 to 1024. We make an observation that network with Laplace vectors learns better, and the trend continues. Also, we observe that point density more than 512, the performance either dips or saturates. We also observe that an average drop of 6.3% is observed when we do not use Laplace vectors for few-shot classification. We perform a further ablation where we find the optimal value of k nearest neighbor for 5-way 10-shot. Graph shows accuracy versus number of k in the k nearest neighbor varying from 10 to 80. Ablations show that k equal to 40 is optimal value for k nearest neighbor for the computation of Laplace vectors. Too large k or too small k also drops the performance. A similar trend is seen in 5-way 20-shot ablation as well. Further, we check what value of curvature is best suited for point cloud prototypical few-shot classification in hyperbolic space. Plot shows accuracy versus hyperbolic curvature varying from 0.1 to 1. For 5-way 10 shots, we observe that curvature equal to 1.0, that is truly hyperbolic, works best. Similar trend is observed in 5-way 20-shot classification task. Table compares performance of all algorithms on point cloud few-shot classification. Our method performs best in terms of accuracy and efficiency. One can observe that all previous models are huge and have large throughput, hence can be considered inefficient. In contrast, our model has a really less throughput and has 170x lesser parameters compared to previous approaches. We also make one important observation that all previous methods have high standard deviation to their experiments. The main reason is because their lack of generalization to novel tasks. Our method is robust to novel tasks with minimal standard deviation. We benchmarked our model on laptop GPU, that is NVIDIA 1050 Ti, and the best part is that our model can be trained on both CPU, GPU and even edge devices like Jetson. Furthermore, we demonstrate results on few-shot classification task on 5-way 10 shots and 20 shots as well. The bar graph compares methods versus accuracy. We can observe that our model with hyperbolic metrics performs better. We also observe that there is a distribution drift in prototypical network causing performance drop when there is less data, that is when the data is dropped from 20 short to 10 short, in compared to our method that shows stability in performance due to this distribution shift addressed by our proposed Laplace vectors and hyperbolic metric learning. Similarly, we do this benchmarking for 10-way 10 shots and 10-way 20 shots as well. A similar trend is observed where our hyperbolic version is performing better, and we can still observe the distribution drift in other approaches and stability in our approach. On further investigation, we observed that there is a overfitting when we do not use hyperbolic metric in GPRNet. We observe a 16.3% of drop in train versus test accuracy to novel tasks due to distribution drift. Similarly, we see a stability to novel tasks when we use hyperbolic metric, and the train versus test accuracy go hand in hand, showing stability. In conclusion, we presented GPRNet, a geometric prototypical network backed by geometric features like intrinsic geometric interpreters and Laplace vectors. Our model is easy and efficient, can be trained on edge devices like Jetson, and is robust to novel tasks. Try GPRNet yourselves by visiting our GitHub page or scanning the QR code. Thanks for watching.
You're mute.
Okay, perfect. So the message was audible. Thank you very much for the nice presentation. We have time for questions. So for the virtual audience, please just write the questions into the chat. We will read them out loud, and then the speakers can respond. For the people in the room, if you want to ask a question, please come forward. There is a microphone here in the front center, and you can ask your question. Okay, are there any questions on Zoom? I'm just checking. I don't see a question, so please write questions in the chat. I have two questions actually. One is you multiple times emphasized that you have a very simple MLP which actually does the classification, and you have some features that you extract. I guess you tried to experiment there with more complex MLP or a bigger MLP or something. Can you give us a little bit of insights if that worked, didn't work, or what your insights are there?
Hello, am I audible?
Yes.
Yeah, so we also tried with very huge parameter models like convolutions and Con2Ds. It worked, but the main motivation was, can we train these few shot learning algorithms on an edge device? So it worked, and it also performed almost equal to what we did with a single MLP. So we thought that this might be insightful, that even large models are not that capable what a single MLP can do. So this was what we found, and that's the reason why we proposed the single MLP variant. Hope this answers your question.
Yes. And my second question would be regarding the use of this Jetson device. And for my understanding, you need that if you want to enable something in an environment where compute is limited. And I was wondering what application you had in mind when you went for that decision.
Great question, actually, though. Our main motivation was we wanted this to be deployed for semantic segmentation or part segmentation task on an edge device, where manufacturing unit is having, where we do the part segmentation of mechanical parts. So based on that, we started our exploration with this small experimentation where can we first do the classification on a Jetson device. Hopefully this worked on very well for us. We hope that we see a segmentation paper also on edge devices like Jetson.
Thank you. Are there further questions? I don't see any on Zoom. Is there a question in the room? That seems not to be the case. Then I have one more question. It's a little bit a nasty one. Sorry about that. You had this visualization here, this one. And I was just wondering, the x-axis is the training progress, or what is the x-axis here?
Yes, the x-axis is training progress. I guess it has been clipped off during the video recording. Sorry for that.
Yeah, cool, perfect. Further questions? We'll check Zoom again. Your last chance to write question. There is one in the Zoom. How robust is it to noise and missing parts?
Yeah, great question, Ali, though. It is robust to missing parts, but unfortunately, it is not robust to noise because in hyperbolic space, the moment we introduce noise, feature drift happens exponentially. So we observed that it is not robust to noise. That is the reason why we didn't benchmark it for data sets like scan object NN and Sydney dataset. Hope this answers your question.
Yeah, thank you. I would have a follow-up question to that. You said it's robust to missing parts. I don't know, like, did you have an intuition on how robust it is? Like, how much can I remove? And are there
A really great question though. In point clouds recently in NeurIPS 2022, there was a paper released called Rethinking Compositionality of Point Cloud in hyperbolic space, where they introduce a regularizer parameter in hyperbolic space, which tries to imbibe and preserve the hierarchy of the data. They do this by simply taking part to complete point cloud hierarchy in a hyperbolic space. This is the reason why even our method is also robust to part-wise or missing parts as well. Because in that case, if you have, let's say, assume we have an aeroplane point cloud and you have a missing tail, still we can consider the entire point cloud as one of the part, which makes sense that it fits into the decompositional hierarchy of the hyperbolic space. And that is the reason why it is robust to missing parts, but not noise. Because the moment we add noise, the topological error increases and the Laplace vector and intrinsic geometric interpreters are really susceptible to it.
Okay, thank you very much. There is also still nobody coming to the microphone. I hope that changes later in the day. Like, really, please ask questions. It's very important. It's otherwise not much fun for the speakers. We will have our keynote in 4 minutes. So there would be more time to ask more questions. I think we should not start the keynote early because there might be people who are just joining for the keynote. So either we have a 4-minute break or we come up with more questions. Also for the virtual audience, please feel free to ask questions. Otherwise, if the keynote speaker is already there, you can test the screen sharing that we are afterwards ready to start.
Okay, I'll try to share the screen. Can you hear me, by the way?
Yes, we can hear you, and
Awesome.
you will get a proper introduction later by Dana, but you can start your screen share.
Okay, just a sec.
So you can see your screen and an animation.
Okay,
Cool. I will optimize the experience. Will you turn your camera on or not?
Oh, I will. I will. Do you?
Yes. Now we see.
Okay. No, good view. Um.
Just give me a second. I wanna.
Okay.
So let's do it this way. Okay, so I would give the word to Dana, who is the main organizer basically of the workshop for a proper introduction of our second keynote speaker. And just for all our virtual participants, especially the keynote speaker, we have around 30 or 40 people physically here. So you do have an audience, but we can't really change the camera because there's so many cables attached to that laptop, and that otherwise we will mess it up.
Oh yeah, of course.
Okay, thank you. So thanks, Yifan, for joining us. So I just have a quick introduction about her. So she's an incoming assistant professor at the National University of Singapore, and her research focuses on applying machine learning and deep learning and geometry processing problems. She's currently a postdoc at the Computational Imaging Lab at Stanford University, and she obtained her PhD from Interactive Geometry Lab at ETH. She received several awards, such as Apple AI/ML Fellowship in 2020 and Swiss Postdoc Mobility Fellowship in 2022. And her doctoral dissertation also has been awarded at ETH Medal in 2022 and the best PhD thesis at Eurographics in 2023. So thanks for joining us in this workshop, and we are very excited to hear your talk. The stage is yours.
Thank you, Dina. Thank you. Thank you for inviting me. Hi, everyone. It's always fun to be the speaker right before lunch. I will try to keep this short, and let's hope you can still, enjoy Vancouver scene, food scene afterwards. So I'm Yifan. As Dina introduced, I'm currently a postdoc at Stanford in the Computational Imaging Lab, led by Professor Gordon Vestine. And I will be next year an assistant professor in Singapore. So that's exciting. And this is me last year at CVPR. And this is also me last year at CVPR. It's unfortunate to not be able to join CVPR this year. It's one of my favorite conferences. And I hope you all get to, take the max out of it. So my interest in research is, there are actually many folds. I am very interested in geometry processing with deep learning. In the last 2 years, I ventured more into the neural rendering side of it, with a goal to actually leverage 2D images as training data. And this allows us to generate 3D using more visual information. And 3D generation with AI is also going to be one of my key research direction in the future. Okay, so for today, I want to talk about geometry structures and why, especially how to use them in our deep models. So it shouldn't be strange, or these concepts that I'm going to talk about in the next few slides are going to be very familiar to the majority of audience here. So in traditional graphics, we have come up with a lot of really useful structures, starting from meshes, points. These are the classics, and they're used almost universally in the graphics pipelines. And then a little bit more kind of less used, but still very useful many times as an intermediate representation or structure would be things like voxels and octrees. And abstract up a little bit, we will have primitives. And then also key points. And sometimes, especially for deformation or articulation, we will have skeletons. And these, as you can see, gradually move to more into this more semantic meaningful domain. And all of these are great examples of how we have integrated or actual structures that we've been using in graphics to allow all kinds of applications. But it's very curious that actually in the recent years, in the domain of deep learning, we're seeing a trend of abolishing structures, especially if you're familiar with something with things like NERF and things like sign distance function, neural sign distance function. They are all adopting a kind of new network, it's no longer new in the world of CVPR, but in 2019 it was so this kind of let's say quite like groundbreaking sort of networks are introduced, and this kind of network are later coined to be coordinate-based network. And what it does is that instead of using a structure, it simply approximates a function that kind of just output whatever you would like it to be from some query that you put inside. And these queries are usually just points or coordinate that we sample in a space. And the output can be different things. It can be the sign distance function, and in that case, for example, the first paper that used this kind of coordinate-based network will be deep SDF, and it uses sign distance function to represent the shape. And then later, briefly afterwards, we have the famous NERF paper, which represent the output of this network will be the radiance, which is composed of the RGB value of a point and the density of that point in the space. And then from there, it's just the explosion of different types of such networks representing different signals we have in the world. And we have in the more vision side of things, we have actually semantic labels that can directly let's say label different areas in a scene, also represented no longer with a grid with points, but rather directly using this function mapping. So there's, of course, behind this, there's a reason for using such structureless network. But in this talk, I'm going to show you that even if we use such new types of network that doesn't really necessarily need a structure, I would argue that geometric structures are still very useful. And the reason are many, and some of them I list already here. And through the talk, I will be probably including even more. These reasons include such structures will actually ease the optimization challenges when we try to train these networks. And also it will provide sometimes almost for free the editing ability that we don't just get from training, overfitting or training a network without structures. And then finally, these geometry structures naturally bring more priors that we can leverage or use to make our geometry in the generation or whatever application we're focusing on more reliable and interpretable, and sometimes just more robust. So in this talk, I will focus on 3 parts of applications where we used geometry structures in different ways. And I will point at or include papers that, of course, I mostly am interested in, and maybe papers I have myself be part of, or papers that I found very interesting, especially at this CVPR, so that you can go and check them out yourselves when you have time. So let's start with the structure in the representation itself. And because I want to have this contrast of what structure can really bring you, I want to start with a structure-free representation. So like I hinted before, such structure-free representation kind of treat the neural network as a continuous function. And this continuous function can represent many things. And we mentioned that one of the things it can represent in order to encode the geometry would be sign distance function. And another popular signal to represent would be also occupancy network, occupancy signal, which means, okay, if this particular point I'm querying is occupied by some object or not. And then, so this kind of network is very popular these days for the reasons I here mentioned below. So first of all, it's very flexible compared to other representations, such as points and meshes, because they are literally, so once you have this network, it doesn't really have a limitation itself. So because this any network can basically be treated as an approximation of any function, you should be able to approximate to anything you like, theoretically, of course. And another thing is that so this function, the network is itself continuous. So the resolution of the signal you're trying to approximate theoretically is also infinite, meaning that so you can query this space as dense as you would like, and you will always get a smooth, or you will get a value out of this function you're trying to approximate with a network. And we'll see that why I kind of try to emphasize this theoretical limitless side of it. So exactly on this note, there is, so any network, as we know, given, there is a capacity limit, let it be defined by the depth of the network or the size of parameters, there's always a cap of that representation power. And when we try to use just one network to represent the entire, let's say, shape, if we're talking about SDF or occupancy, then there's also a cap of how much detail we can, or how much real representation we can encapsulate in that network. So to address this problem of the limitation of representation power, there are different kinds of spatial partitions that people use to the network, to the representation is to be able to increase how much the network can represent in practice. This is we have seen throughout the time, starting from a dense grid that just divide the space irrespective of the signal's location in the space or distribution in the space. It just divides the space into different grid and represent the signal inside the grid with some local networks. And then starting from there, we're seeing a kind of smarter or a more adaptive partition in the space, such as sparse grid and irregular grids, etc. So this is spatial partition. There are also, so what comes with it is not only the high or higher capacity the representation power, rather that we usually desire in a generation or editability, because once we anchor these representational networks signal to some spatial domain and only describe this signal in that local region, then say if that local region also is associated to a certain object, then there will be a way to actually look at that network, that specific local network, to locally change this object. We can do simple operations with such representation, such as removal, duplication, translation, and replacement. So here is a paper that came out almost 2 years ago that kind of represent a scene with a neural field with partitioned actually dense grid, and then it learns how to mask this space with flags, whether, for example, this grid contains an object or not. And then you can move this object or move this particular grid around or remove it, mask it to be not an object, etc., so that you can kind of do different interesting things with this. Then we have, so after this partition the space, we have also other partitioning, more global partitioning. So we have partitioning of a signal into, or a shape into different primitives. So for that, we have BSP network and CVX network. Both of them came at the same time, actually 3 years ago at CVPR. And they kind of encapsulate similar ideas, which is to actually represent a geometry with different different convexity, different planes, so that we have a kind of compositing different planes into a convex shape. And we have also the partitioning in the frequency domain. And here I want to talk about a paper using called implicit displacement field, which came out, well, 2 years ago, or no, one year ago at iClear. So this paper, the idea is actually taken from a very well-known representation in computer graphics, which is called displacement mapping. And here you can see the displacement map is used to generate a large terrain very efficiently from just by adding, so you represent, this is a base shape, a base surface, and it can be mapped to a displacement map with a UV map. And this displacement map is just a 2D mapping with some values on it that simply tells you how far your desired surface gets extruded from your base shape. And we kind of take this idea and lift it in a 3D space. So we will have a representation for like this implicit representation that I talked about, an implicit SDF representing the base shape in 3D. And then we have also a displacement kind of nested onto the space SDF. And by compositing them together in a kind of more integral way, we'll have a composed shape, composed geometry like this. So how does it work? How do we make sure that this separation can happen automatically? So this is the interesting part. We want to be able to do this separation without knowing, okay, which part of my surface signal belongs to the base as smooth surface and which part of it is the actual details. And how do we try to do that without a supervision? The idea is to leverage some intrinsic inductive biases in the architecture of the network itself. And here what we use is a new type of activation in the network that uses sign activation. And because the sign activation has this additional parameters that control the frequency of the network, you can kind of manually define, or even you can kind of evaluate how much of a frequency a certain network actually can represent based on the these frequency hyperparameters you set in the network. So if we manage to, if we set this hyperparameter to be low for the base surface, then there is only this much frequency that the space surface can represent. So all the details will be automatically pushed to the displacement that or the details that we want to represent. And of course, these details are higher frequency, so we use a higher frequency network to with hyperparameter set to support that, to represent this detailed information. So this allows a automatic separation of smooth and detailed surface details without any human intervention. And what's cool about it is that this network is in fact very very small, and we can see that the level of details is very impressive, even though this network is only contains only is only a 3 megabyte large. And the meshes itself are actually millions of vertices that takes a lot more space to even store, and not to mention the transfer. And again, similar to previously mentioned grid structure in the representation, there also comes with such networks are also, or this kind of representation partitioning in the frequency domain, we also have added editability. And in particular, what we can do is that we can transfer details that we learned from one source shape to some other target shapes that have a sort of a similar coarse shape. But say this target is a short or a pair of shorts, and it contains different folds. And by using the previous mentioned networks, we can automatically separate the details from these from the original given shorts and two pairs of different shorts in an unsupervised way. And then we can, with the method I mentioned below, somehow just transfer the details or folds that we learned from the first pair of shorts to the second one. So here, what we do is that because we need to find some kind of correspondences between these two pair of shorts. So instead of saying, okay, this particular P is where I'm going to add this detail, I have to say this particular P actually describes a certain position in my surface, on my surface, and it should describe, for example, below the center of the waistband. And then I should be able to find the corresponding P star in the other shorts, also kind of locate at that place below the center of my waistband. So how do we do this? We can use actually learned geometry or shape descriptor to semantically to encapsulate some kind of local shape descriptor for that position P. So you can try all kinds of things here. What we tried is actually to incorporate some point net type of architecture to describe a local, the local and global position of that point in terms of in the form of a point descriptor. And then we use a 3D convolution to sort of gather that information into the sample in the space. So say have point descriptors lying on a surface, and we using 3D convolution, we can propagate this information to points away from the surface, which is let's say some point that I sample in the space. And then this will give me a pretty good descriptor telling me where I should be looking at in my original space, original shorts for that sampling or correspondence lookup. And so this is another example of how we learn to transfer such spatially variant surface details onto some new vase that itself contains some kind of detail. And when we fit this network, it learns to automatically remove that detail because of this frequency upper bound that I mentioned. And then it also learns to kind of paste the original details onto this new vase, doing this without any UV mapping correspondence establishment. So this is great. So now let's move on to the deformation part of the talk. Again, I want to start with a structure-free deformation. So in the structure-free deformation, what people usually use is some kind of deformation field, which predicts, uses a network to predict an offset to an existing vertex or point sampling. And what you see is that oftentimes, because this translation happens per vertex, and networks are intrinsically a little smooth and biased towards a lower frequency, we oftentimes see artifacts such as, or distortions that are due to, for example, too many degrees of freedom, or there's just not enough regularization energy to fight. And this regularization energy that we, even if we define something something powerful, it might actually work against a perfect reconstruction energy that we want to achieve. So what do people do? Again, there are actually, this is where structures can be useful, even inside the deformation. And the first thing that actually came to be is grid. It, again, is one of the first structure people integrate when the kind of non-structure solution doesn't work. So here we have some examples of using grid or so-called lattice to actually achieve free-form deformation. And the reason why grid is the first thing people think of, or why it can be actually great, is that, so first, of course, we have 3D convolution is a direct adaptation of 2D, the success of 2D neural networks to 3D. So it's not surprising that in order to use 3D convolution, we of course need to use some kind of grid, 3D grid for the 3D convolution to operate on. But 3D convolution is actually nice in the sense that it's able to smoothen out the signals, so that we will be able to get more smooth deformation, which is actually desired in many cases. And because this same convolution kernel is able to scan through all the grids, and with some kind of pooling operation, is able to gather more global context. This is actually, or global or kind of regional context. And this is very useful to have a sort of a semantic notion in the deformation. Moving slightly away from it, we have cage-based deformation. This is different to the previous mentioned grid-based deformation, because 3D convolution is very computationally heavy. And the resolution of this of the lattices will basically have a direct impact on both the size of the network and how much detail we can capture with this the resolution. And so in order to actually disentangle us away from this kind of resolution dilemma, we introduced a cage-based deformation. And this is, again, inspired by the great literatures, many literatures kind of in this domain, in classic deformation, that use cage-based approaches for example, interactive deformation, shape modeling, etc. So here, all these methods they are mature actually tools that are designed for deformation. So they're designed to preserve details. And so we will almost by construction not have the artifacts that I showed 2 slides earlier with distorted chair legs, etc. And then also what's quite great about this this method is the cage. So the deformation parameterization is solely controlled by the cage vertices instead of the shape resolution. So we will be able, as you can see later, we'll be able to actually operate on quite topologically quite complex shapes while keeping the network architecture as well as the capacity similar or kind of constant. So the first step is to learn predict the cage parameters. So given a target shape and a source shape, which we want to deform from, we first learn cage parameters that that kind of defines the cage around the initial or around the source shape. And then what we do is that we will deform this cage and then apply the classic shape-based deformation as a differential layer, which will kind of based on the deformation, based on this initial cage and deform the shape, deform the shape lying within the cage. And as I mentioned before, there are many different ways to actually realize this deformation within the cage, and all of them are already designed in such a way to minimize geometry feature distortion. So as long as they're implementable in a differentiable way in the network, then we automatically get that power from these classic geometry processing tools. And the advantage, as I mentioned before, is that we can leverage many kinds. So here, actually, in this paper, we used one of the simpler kind just for the computational efficiency, but there are many other methods that actually focus on different types of to minimize different types of distortion. And by using this kind of structure, we can tap into that source of that great source. And then another aspect of why we want to actually neuralize this cage prediction is that by having a network exposed to different instances of chair in the data set, and having the network to satisfy all these so the defined loss functions on all these pairs, you will force the network to kind of reason or perform well for on average, all these paired instances. So in a way, the network will have to sort of leverage the alignment of these chairs in the data set. And as we'll see later, there is a reasoning about the correspondence that kind of just emerge from training from a data set. So how do we train this network? And we first, so again, given the source shape and the target shape, we have 2 standard shape encoding networks that predicts the, so in the upper branch, we predict the initial cage parameters, and in the lower branch, we predict the offset to get a deformed cage from this initial cage. And then as mentioned before, we can use standard operations in the classic cage-based deformation to deform this this enclosed shape lying within. And finally, we will get this deformed shape. And this network is supervised without any part supervision signal by simply matching the deformed shape to the target shape by a standard chamfer distance. So basically, we can sample points on this deformed shape and sample points on target shape, and chamfer distance will try to match these set of point samples. And so this itself, without a cage structure, will actually, because it doesn't have any semantic meaningful correspondence, so there is no, let's say we didn't tell the network which point correspond to which point in the kind of deformed shape. Just by doing this alone without any cage will actually give us a very distorted deformation. But with the cage that confines the deformation space to be a very regular and kind of smooth space, this loss will no longer create any distortion. And in order to actually get a good cage, we have this penalization on the cage weights. And then also we have some additional losses to preserve the features even more. These are particularly useful when you're handling a certain type of geometry, say a man-made shape where we want to have a flat surface to remain flat. These additional supervision or regularization can be very useful. So what can we use it for? We can use it for deforming or creating more variations of shapes so that we can have a more kind of automatic way of generation of a large stock of 3D data set. And you can see that when we compare with previous deformation method, the deformed result is much more reasonable and a lot more, I'd say, practical in the sense that they might not match this target shape as well as, for example, these vertex-based method. But I would argue that these shapes are more, they look more like chairs and cars. And another useful thing we can do with it is that we can tap in or kind of leverage the fact that these cages are not really tied to the particular vertex within itself. So you only need some global context of this the shape within. So we can once we train the network, let's say to deform a human, we can swap in this human to another kind of topologically similar, so kind of humanoid type of mesh that has a very different meshing. But because we don't care about the meshing itself, the cage only cares about the global structure. The learned deformation will still work. So you can see this skeleton can be using the same network, deformation network, without having to retrain. We can use that network to deform a new type of character. Same, for example, this robot also gets deformed to match the target poses. And there is one step though that we need to do. We need to be able, so because these are the human and for example, the robot or skeleton, they are different. So the initial cage need to be slightly adapted to fit that, to fit the different, so to fit this new character. So here is the optimization that we need to do beforehand, and we just need to do it once for any new character, and then the deformation will be free. So in this optimization, we basically optimize this the vertices of the initial cage so that the for a very few selected corresponding points shown at this dotted place, their cage coordinates or weights remain similar or the same, hopefully the same. And again, just to emphasize, this optimization just need to be done once, and then we can use the same initial cage that we have obtained for the subsequent deformation. And from cages, we actually, there are a lot more similar idea emerged from this kind of structured deformation. or sort of, you can see the cage as a hybrid way to, or kind of a hybrid representation on top of, say, a mesh, a point, or even later, as I'll show, on top of an implicit field to guide the deformation. And we have, for example, using a key point to guide the cages for the deformation itself. And cages are also used directly in a trained neural radiance field. And then we have, we can use the key points, or in human body, these key points are usually referred to as joints for deforming, for example, shapes, but also deforming trained human faces or avatars, as I'll show later. And we can actually kind of build a tight mesh directly in the scene and use that tight mesh to drive the deformation itself in a user interactive way. And I just want to quickly mention this paper that is at the CVPR. It's very interesting. I just actually, I was quite, yeah, really excited by this idea of actually starting to use dynamic information from the input. And here, what they do is that they are given a sequence of images, or given a video. They automatically learn some key points to define the motion node of in the scene. And then they're able to associate the radiance field with these key points. And then later you can kind of manually, drag these key points around to let it play, let it sort of create a dynamic of the scene. And that's very interesting. And also at the CVPR, we'll have a paper on 3D representation or for an animatable avatar directly reconstructed from a monocular video. And here there's actually two kinds of structure so before we have kind of this line of approach usually is built on either mesh, that will be one type of structure, or not using structure at all, meaning that you use some kind of implicit surface or a neural field to represent the geometry and appearance. But here we use the first point to a colored point to represent the appearance and geometry. And then we kind of tie it to a 3D 3D morphable model. And then we leverage this tied 3D morphable model to allow faster and more efficient animation. So here is an example how this can be quickly animated, and how these points actually give us a sort of interpretable geometry so that we can get the normals. We can apply different shadings on top of it. Okay, finally, I'm already a little bit over the time, so I'll go over this rather fast. I will talk about the generation part of things, which is actually the most interesting part. So here, without structure, generation, we can just generation is like tossing a dice. It kind of all depends on some randomization latent code. So the limitation is that it works really well actually on aligned data such as faces, but there is a lack of also, so it doesn't necessarily work well on human bodies, exactly because there are so much structural changes and deformations that just makes the network in networks has to model this additional deformation, which is super hard. And then of course we also don't have actual control, because all we can do is to change the latent code, and then you'll just get another identity, but sometimes we just want to change the facial expression. So what people usually do, especially in the domain of body, is to incorporate parametric templates that we have developed before. The most notable ones are simple models, as well as its extensions like simple H and simple X. And for faces, we have something called Flame, which is also quite used a lot for facial modeling. And so what this model does for us is that it can allow us to generate this to let us generate the change of the human, the appearance, the shape purely in the canonical space. And then the deformation can be kind of controlled by this parametric model that we have in addition as a control input. This makes the generation much easier because we're in a confined canonical space. And actually most of the paper are operating in this canonical space. And just, you know, in the CVPR, you'll see a lot of things about diffusion. And in 3D diffusion, what people do to create avatar is basically take this more kind of general idea of using 2D image diffusion for 3D, like dream fusion sort of idea, and then use an additional shape prior to enforce that shape to be more like a human. And this is again, then so here we're using either simple or flame, and we have all these kind of new concurrent papers coming out. Some of them are going to be a CVPR and some of them are archive. They're very fun, but so here the simple shape prior are used both for initialization of this neural field as well as regularization. And for avatars, head avatars, there's a more kind of, it's easier in a sense because because of lesser or less dramatic deformation. So people tend to either so there are actually more work that directly pans the face by optimizing the textures. So here we have clip face and dream face, for example, they're going to be introduced as SIGGRAPH, which produce really amazing results just from text prompts. And in terms of object level 3D generation, these structures are also useful. So when we have structures in object, they're usually parts, different parts. And these parts can be either learned or kind of divided in an unsupervised way. And again, I want to highlight a few papers that are coming out. The CVPR is, for example, PartNerf, and also, well, these papers are from before, but they're using sort of this leverage. They're using the data set PartNet to sort of, you know, divide the space into different parts. And then what is even harder is the scene scale generation. And here again, people used grid as the first idea. And but what is quite interesting and what come out this year CVPR is Disco Sim. And you will see that it uses bounding box to sort of look at object level neural field and then compose things together in such a way that it follows a layout prior, and it also follows through the background and foreground compositing. And finally, I want to say, come back to the original question. Why and how do we use geometry structures in this in deep learning? So the why is that these structures are great 3D priors that we can use to just improve our result. And oftentimes come together with these structures are better editability, let it be deformation or let it be kind of compositing. And finally, these structures usually, and some of it, as we have seen before, they are mature methods from the classic computer graphics literature. So they're already really good properties that we can directly use. And how do we use them? As we can see before in this talk, there are actually usually two ways. One is directly use it as sort of a hybrid representation on top of what your original representation. And another way is to use it as a sort of factorization for this for your network parameterization. And especially as a final words to folks with background in graphics, I will say that this is a great time for you all because just look at how what are the generation results from Adobe Firefly if I give this text prompt, a girl counting 3 with her hand. This is what I get. I get 2 hands, a girl with 3 hands, 4 hands out, but in total 4 fingers, and 3 and 5. So there is generally, so diffusion model, these are all stunning results, visually amazing. However, there's just a lack of geometry and physics that currently this diffusion model or impressive AI tools are still, they seem to be quite blind in that area. So this is where our knowledge in the graphics and geometry structure can be extremely useful. Yeah, okay, so that will be all of my talk, and I look forward to questions.
Okay, thank you very much. So if there is any question from the people online, you can just write it in the chat.
Hello, can you hear me? So
Yeah.
very, very nice presentation. So I'm Dino Yang from SFU. So I'm very interested in the 3D generation question. So for the 3D generation, so for the current researches, for example, if we apply the diffusion model on the SDF grid, or people are using the tetrahedral grid to do the diffusion. So we add the noise independently on the grid or the discretization of the SDF grid. So there is, I mean, almost no 3D geometry prior through the diffusion process. So before we reach the final point of the diffusion, inversion process, so all the internal process we can simply break geometries. So it is quite easy to get like broken geometries or meshes, especially topologically speaking. So I think it is for like we get more geometry prior, especially along with the diffusion process. For example, if we consider the something like geometry evolution or curvature flow, we can integrate curvature flow into the differential equation or stochastic differential equation in the diffusion process, that we can kind of guarantee mathematically that for every step of diffusion, we can get something like a valid geometry in the diffusion process.
Yeah, I think I honestly haven't thought about this, but I think you tapped on a great actually research direction, because I think the one current limitation for applying 3D diffusion for 3D types of data is that there's no, we have to kind of simulate or create the intermediate steps in a way. So if you look at the diffusion models applied to 3D, they have to build these, noisy, let's say SDF grid that kind of is not, it's intermediate representation as SDF grid, but in order for the diffusion to happen and operate on that representation, one must create these data set. And this is a very kind of cumbersome and annoying pre-processing step people have to do. But what you mentioned before is great, because you're using sort of physics and simulation to actually create these intermediate steps. And I think, yeah, this is a wonderful kind of direction to pursue. And I would think that maybe it's not, maybe it definitely has its limitation, because we cannot really get such simulation for all kinds of application. But yeah, when we, and maybe we don't have, it's not easy to get cheaply, this kind of simulation for all kinds of signal that we want to represent. But this is definitely a very exciting place to venture into.
Thank you. Thanks for your comment.
Okay, great talk.
So I was wondering how to handle collision, right, using those cage-based representations. I like the fact that you mentioned hybrid representations, right? So this, do you think there's a potential to combine implicit representations to handle?
Yeah, for the cage-based deformation, there were actually there was no integrated laws to penalize any penetration. And when we explored with just ShapeNet architecture or ShapeNet kind of shapes, we actually see the cage move very little. But as you pointed out later, for the articulated shapes, like the skeleton and things like that, yes, the cage will actually introduce collision. And I think, for example, the CBXNet and BSPNet that I briefly mentioned before, that uses partitioning of space, kind of like actually implicit function in a way to represent the geometry. There is actually a very simple way, like you said, to detect collision. And I think these deformations can be hopefully combined together. Like again, we have some, for example, in a cage nerve or deformed cage when a deformed nerve with cage paper. I think that will be a example of how different kinds of implicit and cage based deformation can be combined.
So those were the two in-person questions that jumped up. There was one more.
Hello, can you hear me?
Mm-hmm.
Yeah, thank you for the talk. I just want to get your view on a few things. In particular, I think you mentioned about deformation through the cage-based like methods. But you also like kind of touch on like different types of representation. For example, the lower levels, I think the cage is more on the lower level side of deformation, like directly. You know, you build a cage on top of a mesh. Like, what do you think of like in a general setting? Is it easier or like better to do deformation through the lower level representation or like higher level representation, for example, like key points, skeletons, things like that?
Yeah, great question. I think it's really application driven, and in my opinion, I wouldn't really say cage deformation is less high level than a skeleton deformation. In fact, they are so interchangeable depending on what kind of articulation, what kind of deformation one wants to achieve. In fact, if we look at furnitures and if we want to sort of change the depth of a table, cage would be kind of a better suited proxy than skeleton. So I really think it depends on what kind of deformation we want to focus on. And then if we actually want to tackle the entire scene, there are different kinds of deformations. How do we, choose the correct node for what kind of representation to use? And I think our sort of AI assisted deformation or graphics pipeline will be kind of more systematic. It will be more like a system that you have actually a first step of choosing the right tool. Maybe that choosing itself is an AI step. And then how do we apply? So then after choosing the tool, how we can then use all these sorts of specialized method to apply that chosen tool to that specific node.
Okay. Yeah, thank you for that answer. Also, I wondered, what do you think about like part segmentation information? I think in the end, you kind of touch upon works that are trying to model parts. Like, what do you think? Like having the part segmentation information would somehow like, I don't know, like be assisted for like more principled deformations or like. things like that. Like, do you think, these segmentation information are just like something nice to have, or is it something that's going to be critical if you really want to do, let's say, more fine-grained, deformation, or application driven? I don't know.
I think actually parse annotation is wonderful. I would use it whenever possible, because usually I think, okay, if I move back to the, if I have the slide about this for different part, what we essentially I think want to do is to be able to integrate whatever we came up with these automatic tools and use it in a human way. And we human actually, we have a semantic in our mind. So these labels actually, I mean, so if we don't have these labels, we will probably have shape partitioning that sort of conform in the sort of separation in the space where there might be some semantic emerging, such as left arm map to left arm. But with these labels, I think first, okay, just from this deformation quality side of things, with labels, we can have better correspondences so that we don't map, the chair handle to the right chair handle to the right side of the leg, even though they are Euclidean space are close. But with these additional handles, we'll be able to, hopefully change just, for example, the handle of maybe just one chair, and then we can have all the handles of that similar chair changed. So I think the more kind of semantic motion we have, the easier it is to conform with our human mind to actually make the editing more kind of intuitive.
Okay. Yeah. Thank you for that. That's a great answer. Thank you.
Are there further questions, perhaps also from the Zoom audience? That's not the case. I would just thank you again for this very nice presentation. And you can put. Yes, let's first say thank you again, and then you can ask your question. Everybody who wants to go for lunch can go for lunch. But yeah, we will go to your question. Yeah, please.
Oh, hi again. Sorry, just a quick follow-up. Do you think there are any what might be the challenge in your opinion of learning these parts in semantics and geometry models purely from data? Because there's ample amount of data online, whether it's images or videos on YouTube. What would be the main bottleneck for learning, let's say like a model that has parts information and geometry, fine-grained geometry? Like, do you think it's like a multi-step thing? You first extract something, and then later on you build on like based on what you have, you further analyze it, and then have certain I don't know, like parts semantics built on top? Or is it more like learning everything, you can end-to-end learn just everything from scratch?
I think you answered your own question. I think you mapped out two different ways, and actually I would argue that there are different schools in depending on their resources. They might follow different actually ideas. In last year, I actually have a paper sort of trying to go to the second route, which is just trying to have one network that predicts everything. But my personal opinion or my personal take on that, it's such a network, to build such a network, we need so much data and so much, otherwise it will overfit. And it's extremely hard to train. And then so if something goes wrong, I don't know where to change. I don't know what step is missing. So my preference is actually be more kind of explicit, build things step by step. So I'm kind of a follower of your first idea.
Thank you.
Cool. Any further questions? Otherwise, I think we should call it a win for the morning. Thanks all the speakers, thanks all the keynotes, and we will reassemble at 1:30. So please enjoy your lunch and see you all later. Thank you.
Thank you very much, Ivan.
Of course.
Okay, hello everyone. Let's start with the second half of our deep learning for geometric computing workshop. We will start to the second part with an incredible keynote from Theodore Kim, who is an associate professor of computer science at Yale. He will talk about synthetic training data. Is it a bad idea? So Theodore Kim is an associate professor in computer science at Yale University, where he investigates biomechanical solids, fluid dynamics, and topics in geometry. Previously, he was a senior research scientist at Pixar Animation Studios. He received a PhD from University of North Carolina in 2006 and a BS from Cornell University in 2001. He has received the NSF Career Award, multiple Best Paper Awards, 2 Scientific and Technical Academy Awards, underlined. Our teams have appeared in over 2 films, and he has screen credits for Cars 3, Coco, Incredibles 2, and Toy Story 4. That is an incredibly awesome bio. Thanks for being here. Thanks for the being in our workshop, and the stage is yours. If you can share your screen.
All right, here I go. I'm going to try to share my screen. Can you all hear me?
Yes.
All right, here I go. I'm going to try to share. I'm on a really shaky hotel internet connection right now. So let's see how we do. Let's see how we do. All right. Okay, can you all see this?
Yes, great. Thank you.
Okay, great. All right, great. Thanks for the introduction, and hi everyone. Thanks for coming to my talk. Yeah, sorry I can't be there in person. I like I said, I'm on a shaky internet connection, but I think that I sent you a recording of the talk in case like something horrible happens and it just like totally dies. Okay, let's get to it. As the title implies, today I'm going to ask the question, is synthetic training data a bad idea? All right, so there's lots of reasons that people want to use synthetic training data. It's like cheaper than going out and getting real world data for one, and real world data can be really messy and noisy. So one very important factor, and this is getting a lot of attention, is that bias in real world training data, it can appear in one form or another. So, you can download training sets and they can insidiously be like, reflecting of various biases you see out in the world. So you download a data set and unbeknownst to you, it overrepresents men, overrepresents like white people, or overrepresents East Asians. And then you try to learn off of them, and all these biases, they then get inherited by your algorithm. So one of the big papers on this that I'm aware of is the gender shades paper. So this paper showed that there's 2 major data sets that are overwhelmingly white. And there were 3 major commercial facial recognition packages that had like really awful error rates when it came to recognizing Black women in particular. So of course, this is a computer vision workshop. So I suspect that all of this is not really news to any of you. So synthetic training data seems like a pretty good idea, right? You can control the distribution of the data. You can make sure it's not just all white men or Asian men or cis people, and your learned model should be all that much better, right? So it seems like a pretty good idea. There's an assumption here, though. So the assumption here is that synthetic training data must somehow be inherently unbiased. So the algorithms that are used to generate them, these are assumed to be universal in some way. So it's assumed that they like capture the fundamental physics of the external world somehow, and then they just apply those fundamental physics in some magical way, and through computation, you get these nice cleaner data sets up on the screen. So more specifically, the assumption is that computer graphics has been around for a long time. So it's been around since like at least the 1970s. So we've been refining our notion of how to digitally represent reality for at least 50 years. So this is actually the 50th anniversary of SIGGRAPH this year. So that's the major conference where all of these computer graphics algorithms are usually published. So we've been refining this notion for 50 years, and every year we strive for like a more perfect depiction of reality. And the assumption is actually that we're pretty close. So we're so close that you can actually use the output of these algorithms as inputs to more sophisticated algorithms. So I recently read this book, Image Objects by Jacob Gabouret, so shown right here, which it raises a different perspective. So I want to talk about this perspective today. So what this means is I'm going to talk about lots of computer graphics history for like the next half hour or so. And I know this is a computer vision conference. I promise you I'll bring it back to computer vision and deep learning at the end. So Gabouret, he's actually a film and media scholar at Berkeley. He's not a computer science person. So you're going to see that I have to like correct his quotes a little bit just so it fits our nomenclature a little bit better. But he wrote a scholarly book about the early days of computer graphics. So this is early days of computer graphics. So this is back during Ivan Sutherland era. This is University of Utah days back in the 1970s. Again, I realize you all are a computer vision conference, so not everyone is going to know this. But all of the basic computer graphics algorithms, they came from the University of Utah back in the 1970s. So it's not like MIT, it's not Stanford, it was Utah back in the 70s. So in computer graphics circles, this is well known. So this is accepted historical fact. It's not just me making this up here. So Ivan Sutherland, pictured here, he won the Turing Award for his contributions on this in 1988. All right, so it's not something that's in dispute, and I'm not going to be disputing this here. So we can take this as pretty good fact. All right, so again, if you're in the hit SIGGRAPH at one of these like book vendors, so I bet it's actually on sale at CVPR as well. So let's see one quote from Gabouret's book. So realism is unevenly distributed in any given rendering. He actually says simulation. Like I said, he's not a computer graphics researcher. He's a film scholar. So he says simulation. If you read the book, though, he means light simulation. So colloquially, we think of that as rendering, right? So realism is unequally distributed in any given rendering. So back in the 1970s, it's actually not really hard to see this. So actually, there was only a few things that you could render like at all. So this is Marcia Sutherland's VW bug back in the 1970s. And what you're seeing here is there were a bunch of grad students that were just very crudely digitizing this. So the faculty in charge of the University of Utah lab, like I said, was Ivan Sutherland. This is his wife's car, Marcia Sutherland. All right. And they're using just like tape and yardsticks to actually digitize this thing. So the fun part of this story, which Gabouret tells in his book, is that it actually took like a few weeks to scan this thing. So in the meantime, Marcia Sutherland actually was driving around Salt Lake City with all these markings and stuff all over her car. So you can actually see this VW bug show up in a lot of early computer graphics papers. So reality is unevenly distributed here in that, yeah, you could only render like one thing, like a VW bug, all right? So the focus on automobiles here, though, back in the 1970s, this is actually not unique. So this was sort of a fun and interesting data acquisition exercise for the University of Utah grad students. But actually, new algorithms for computer graphics, they were being developed. They had been developed for decades, not in the US, but in France by that point, in the automotive industry in France. Whoops, sorry, wrong direction. All right, so specifically, Pierre Bézier was doing work at Renault, and Paul de Castilloux was doing work at Citroën. So this is a shape workshop, right? So I'm assuming you've at least heard these names before. So you probably heard the name like Bézier curve and de Castilloux's algorithm. Yeah, it's those guys. All right, so you've probably heard these if you've taken like any course on solid modeling before. And this is indeed where they all came from. This is the French automotive industry back in the 1950s. So if you actually look at Pierre Bézier's page, there's on Wikipedia, there's stuff asking like, so what was Bézier up to during like the Nazi occupation of France during World War II? Like he was a grown-up, you know, during the Nazi occupation of France in the 1950s. So you know, that's how far back all this goes. So this is an image from an article that Bézier wrote back in 1971. So let's look at the title. So an example of an existing system in the motor industry, the Unisurf system. So it's an existing CAD system that had already been in a wide use by 1971. So lots of interesting computer graphics-y stuff coming out of France, going back to the 50s. This was known to the people at University of Utah. This was known by Ivan Sutherland back in the 1970s. All this interesting stuff, it's happening over in France. Paris is this hotbed of graphics innovation back then. Let's get some of the students from over there and bring them over here so that we can get some cross-pollination of computer graphics specialties. And he was actually very successful at this. He brought over two names that if you've taken a computer graphics class, you've probably heard before. All right, the first one is on the left here. This is Henry Garreau. This is the person who gave us Garreau shading. Again, I know this is a vision conference, so maybe you don't know this. I guarantee you you've played a video game that has Garreau shading in it before. So it's probably like running on a chip in your phone right now in your pocket. So this is how popular it is. And the other one is Buituang Fong. So this is the creator of Fong shading, Fong interpolation. And again, I assure you that even if you don't know what these algorithms are, you've played like a video game with this. In fact, if you've seen Toy Story, like Toy Story is all Fong shading. So you've seen Fong shading a lot. So when he's remembered at all, Buituang Fong, he's remembered as a Vietnamese grad student who happened to be at University of Utah. He was actually brought over from France, though. Like I said, he was recruited because all of the interesting stuff was happening over in France at the time. And that's because up until the 1950s, Vietnam was actually a French colony, right? French Indochina. So that is the connection between Fong and France. And he moved to France in 1965 to the Grenoble Institute of Technology. This was the first year of the Vietnam War. So I don't actually know the circumstances surrounding his immigration. And in fact, there's not a lot of history surrounding Buituang Fong because he actually passed away very young. So he may have fled because there was war. He may have immigrated for educational reasons. But to be honest, it was probably a little bit of both. Vietnam was not that great a place to be at in 1965. So it would have made sense that he decided to move his family. So he came to the United States, recruited by Ivan Sutherland to Utah in 1971, and he invented Fong shading and Fong interpolation for his PhD dissertation. And this stuff is still used today, right? Like I said, it's probably running like on a chip in your phone right now. There was a SIGGRAPH paper about it like last year. And like I said, a lot is not known about him. He died of cancer back in 1975, but this is part of what he did back in the 70s. He came over because all the hot graphic stuff was happening over in France in the 1970s, and he was recruited to come to the United States. So we go back to Marcia Sutherland's car. We can think of similar industrially manufactured items that were the focus of early computer graphics research. And here I do need to mention that most of the funding for this was coming from the military. So this was military funding was the source of almost all of this research. It was in particular DARPA. This is the Defense Advanced Research Projects Agency. They were funding this. They're also the same agency that brought us the internet. You can see this elsewhere in the 1970s research. So Marcia Sutherland's car was being digitized, but that wasn't the only object being digitized by the Utah folks. So here we see a figure from Ubure's book. So like I said, okay, it says figure 3.8 at the bottom here. Anytime you see this, this is because this is from his book. And you can see that it says model plane. All right, so this is model plane. I see this, and I'm pretty sure actually this is an F-4 Phantom II. So this was a very popular fighter jet back in the 1960s. It was very popular in that it was literally the one that was the most popular for dropping bombs in Agent Orange on Vietnam. So that is actually what it was doing at the moment that it was being digitized. So we can't really escape the colonial and military incentives that drove all of the technological R&D attention back when computer graphics was first made. So there were some really specific applications that were of interest back then. And we're going to take a brief peek back into the analog era to see what those applications were. All right, I'm going to show you actually a scene from the 1970 movie Tora Tora Tora. None of this is computer generated. All right, I'm just going to show this to make a point. Tora 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 is a movie about the Japanese attack on Pearl Harbor. And the scene I'm going to show you is there are a bunch of fighter pilots on a Japanese carrier the night before the attack on Pearl Harbor. And they're all, of course, really nervous. They're all waiting for like the commands to be given, like we're a go for the attack. Let's all launch. So they're all nervous. And this is what they're doing as they're waiting. So let's watch this clip. All right. There's some people underneath the plane, and they seem to have like a tapestry of some kind. All right, he's peeking into a bombing reticule. All right, he's peeking into the bombing reticule. There seems to be a painting of some kind. All right, this is actually a simulator. All right, he's looking into the bombing reticule. He's actually doing a simulation. So he's practicing dropping bombs on Pearl Harbor. So it looks like I'm beating up on the Japanese here. Like this is how everybody did like their bombing simulations back during World War II, right? Even the Allies and everyone else in the Axis. All right, let's look at one specific frame from this, and we can see an analog version of what Gabriel was talking about. So reality is unevenly distributed in this painting. So where was all the effort actually expended in this painting? I'm going to argue that it's in the ships, right? So the ships look the most realistic here. For example, you couldn't like just approximate these as a dot, for example. That would not serve the training purpose of this painting. The water, on the other hand, I'm going to say that the water is where the least amount of reality is actually clustered. So it's just kind of an afterthought, right? It's just this wash of blue. Whereas like all the waves and the foam, doesn't matter, right? For this application, they don't care about that sort of thing. So one element of reality, the ships, it's being highly accentuated over other elements like the water. All right, so here is another sequence from the same movie. This is the actual attack on Pearl Harbor. So this is not a simulation, at least within the reality of the movie. And what we're going to see is him dropping a bomb onto the ship. All right, if we're being real, it's not actually the ship. It's like a scale model on a Hollywood soundstage. We're not going to peel that layer of the onion. All right, okay, they pan over. You're going to see it's the USS Arizona. People back then would have known this was the great success of the Japanese attack on Pearl Harbor. They sank the USS Arizona. All right, now you see it. He looks through the bombing reticule. All right, and within the logic of the movie, this is a success. All right, he successfully bombs the USS Arizona. Okay, again, let's look at the shot of what he actually saw through the bombing reticule. Again, look at the water, all right? There's lots of different reflections and lots of waves and stuff going on here. And let's look at that rendering from before, all right? So the reality of the water is way, way off. The reality is unequally distributed in this rendering. All right, this movie is literally from the 1970s. It's none of this is CGI, so why am I even talking about this? Well, I think that this sort of uneven distribution of reality, it actually is inherited by computer graphics today. So this was Gabriel's thesis as well. All right, so let's go forward to today and let's look at like NVIDIA's Drive Sim app. This is just an example. I'm not necessarily trying to beat up on just NVIDIA. All right, so this is powered by Omniverse. This is supposed to be a simulation of reality, right? So it even says it like right on the webpage for Drive Sim. This is supposed to be synthetic data for self-driving cars. Okay, so let's watch a clip that actually comes with the Drive Sim app for NVIDIA, keeping in mind that research attention has been like lavished onto automobiles since at least the late 1950s. So there's at least like 65 years of research that have gone into making cool looking automobiles. All right, so let's play this. Okay. Now, one of the things is we've all been kind of like trained to watch these videos in a certain way. But I'm going to posit that the reality in this rendering, it is also very, very uneven. So look at the car. The car looks great, right? Credit where credit is due. The car looks great. The reflections are beautiful. You can see like the little inner reflections in the headlights and that sort of thing. The little LEDs on the front grille. It's gorgeous, right? This is not a surprise. So Bezier curves were specifically invented for the automotive industry. So the rendering of the car here, it has the full force of all of computer graphics history to back up its reality. So let's look at stuff that's a little bit off to the side though, right? So let's look at like the dirt, like the trees, like the road. They look okay, right? They don't look as good as the car though, right? So they're kind of flat and low poly and like no one is like burning like RTX ray tracing cycles on like the guardrail, right? They're burning it all in the car, that sort of thing. So again, the distribution is uneven. Now you might have an objection to my characterization of this and say like, yeah, but that's a labor allocation problem. So maybe the modelers and the lighters, they got the word from up on high that you want the car to look cool, right? So just invest lots of time in making the car look cool. And if they had been given a different order, like, well, make the trees in the dirt look cool, then the trees in the dirt would look, just as good, or maybe better than the car, because the car did not have as much attention allocated to it. Is this true though? Okay, let's like look at the most quotidian thing. So like on the left, right, we see this dirt like right behind the guardrail. So is this really true? Is dirt rendering actually like really easy? And if someone had just said, yeah, make the dirt look really nice, then they actually would have succeeded. So this seems really silly to ask, right? Is he seriously talking about how dirt looks? All right. Granular material rendering is actually really hard. So if you look at this paper from SIGGRAPH in 2015, first of all, let's look at like the powerhouses that were needed in order to write this paper. So right, so Disney Research, KIT, ETH Zurich, Cornell, Dartmouth. All right, this is a lot of firepower to write this paper. And also we know that actually they had access to like really mega hardware to do this sort of thing. So they had access to like compute nodes with like terabytes of RAM. All right, and even with that, all right, along the bottom here, I highlighted in red, but it's still a bit tiny. You can see that actually rendering one of these images took 50 hours. All right, so that's how long it takes. And you can see that this was like 50 hours was like the good result from this paper. If you don't have the result from this paper, it takes over 600 hours to render a single image of good looking dirt. All right, so it really, it's really out of the question to in real time get dirt that looks as good as the car did. All right, so now you might say, yeah, but who cares about dirt? I care about the cool looking car. And that is my point. All right, so you and every other graphics researcher since the 1950s have decided that what we care about is a cool looking car. Who cares about dirt? But if we were really going to be huge nerds about the way the dirt looked, I think it's hard to escape the idea that the dirt here is not as good looking as the car. So like, where are the little ground up pieces of like smashed up windshield and like headlights that you just know that are in the dirt by the side of the road? That's not there at all, right? And this car is zooming by, that the dirt would like shift a little bit as the car zoomed by. That's not there at all. All right, so what if instead of automotive designers, the first graphics people had actually been like geologists or botanists or like agriculture scientists, that sort of thing? I think that the reality in this image would be distributed much more differently. So this image, this encodes the history of who made these algorithms, and the distribution of this reality, this mirrors what those people actually cared about. So they cared about cars and fighter jets, all right? These cars, these fighter jets. All right, again, you may have a very legitimate objection to my characterization of what's going on here. So what I'm really looking at is just incentives from the 1970s, all right? We've come a long way since then, right? Since the 1970s. So people can render lots of different stuff. They can render stuff that's more than just cars and planes, right? This was actually true in the 70s as well. Okay, so even before the VW bug was being rendered, like really boring quotidian household objects were being rendered too. This is a super famous one, right? Utah teapot. So this would actually be like exhibit A for like a household object that's actually being rendered. So VW bug, this is a fun historical footnote. Utah teapot is not a fun historical footnote. In fact, you can like go to Google and you can get the Utah teapot in like 10 seconds. You can find a WebGL app that has a Utah teapot like super fast. This is amazing, right? So this data that was scanned back in the 1970s, you can still find it like and load it up in WebGL. It survived that long. This is amazing. Okay, so this idea that like we can render everything, even in your house, your car, the plane, whatever, this was being promised very early on in computer graphics. So even back in the 1980s, even before like ray tracing was a big thing, Pixar, my old employer, they developed the raised image rendering architecture. All right. This is a classic paper. It has like over 600 citations. This is pretty well known in the computer graphics industry. This was the scanline renderer that was developed for Lucasfilm. by the people that would become Pixar and eventually became RenderMan. So if you've seen like Jurassic Park, you've seen like Terminator 2 or Toy Story, this is the architecture that was used to actually render all of those movies. It was also used for this. So this is the short film Luxo Jr. This is a short film that Pixar released back in 1988. And I'm old enough now that I do have to point out that, yes, this actually is the lamp from the beginning of every single Pixar film. So it is that short film from the 1980s, Luxo Jr. And this sort of this makes the opposite of my point as well, right? So this is another household item, not just fighter jets, not just cars. This is another household item that you're able to render, right? A desk lamp, literally the thing just like sitting on your desk. So it seems like we actually are getting closer to depicting all of reality, right? Everything in reality, not just cars and jets, like the stuff literally just on your desk. Okay, let's go back to the original paper from Pixar. It was called the RAISE Image Rendering Architecture. This was actually a cheeky reference. So RAISE refers to Point Reyes. This is like a park, a national park that is that was by the Pixar offices at the time. But it's cheeky because actually they said, oh, it refers to something else too. So it's an acronym. It's an acronym for render everything you ever saw. All right, so there, right there, it's promising it, right? It renders everything in the world, right? So maybe later we can use this for synthetic data. No one said that, but it's implied in this, all right? So everything you ever saw, not just cars and jets, seems like a pretty good foundation for later on rendering some synthetic data. Okay. What if this isn't true though? What if it wasn't made to render everything you ever saw? Right? What if it's not RAISE? What if it's RAISAB? RAISAB. I couldn't come up with a nicer acronym. RAISAB. All right. So what does RAISAB mean? All right. Render everything you ever saw at Bob's house. Who's Bob? All right. We'll get to that. But let's imagine this is true. It only renders the stuff at Bob's house. Hey, Bob. This algorithm, it doesn't render everything that I ever saw. This just renders the stuff from your house. There's different stuff in my house. So if I train an algorithm on this data, is that algorithm just going to do good when it goes to your house and then it doesn't do as good when it comes to my house? So we can see little pieces of this even going back to the 70s. So this is the original Utah teapot. And the story is that Martin Newell, this was the grad student who digitized this at Utah back in the 1970s. He was looking around for something to render, and his wife pointed to the middle of the kitchen table and said, "What about that thing?" And it was just a teapot that was sitting right there on the table. All right, so at this point, we're not rendering the stuff from Bob's house. We're rendering the stuff from Martin's house. And actually, the VW Beetle that we saw before, this sort of fits into the story too. So this is not from Martin's house, but this is Ivan's house, right? Ivan Sutherland. So if we count his driveway as part of his house, then it's part of his house. All right, so we're not rendering the stuff from Bob's house, we're rendering the stuff from Ivan's house at this moment. All right, I'm gonna, a really big quote. All right, don't read it right now. I'll read it along with you. There's a quote from Gabure where he talks about how these everyday objects back then became the test object for rendering during Utah days. Again, I've replaced simulation with rendering here in the quotation because Gabure is a history scholar. He's not a CS researcher. But let's go ahead and read this. We find a proliferation of everyday objects that speak to the culture of the individuals that reproduce them through rendering. These were the objects that were ready to hand as researchers began their work, and in that moment of recognition became transformed into objects of study to be graphed and modeled mathematically. All right, now again, you could say that this was back in the 1970s, and we're way past that. We're way past just like teapots and VW bugs right now. So what does that Gabure quote even have to do with anything? Okay, in fact, you could you can find some like news articles that potentially contradict my thesis here. All right, a prime example of this could be there was a bunch of articles that came out like in 2014 saying, hey, you know the IKEA catalog? The IKEA catalog is actually, it has quietly become almost all CGI. It's 75% CGI. So I'm sure the number is much larger now, right? So here's a Fast Company article written back then about, hey, did you know that actually we fooled you? The catalog is actually all CGI. They didn't even have to tell you. That's how good these algorithms are. And actually, Gabure, he talks about this exact article at the end of his book. And it's supposed to be a, quote, striking reversal of the uncanny and the homely. And this is supposed to dramatize the triumph of computer graphics. So we're not just looking at cars, we're not just looking at fighter jets. We started from a teapot, and now we can do everything, right? We can do everything in this kitchen, literally everything in the entire furniture catalog. Okay, this is the characterization of these news articles and actually of the book. And something actually doesn't sit that well with me about this characterization. I actually asked Gabure about this. Is this what's really going on in this rendering here? All right, so is it that we've advanced so far that we can depict everything in the entire IKEA catalog? But is that really all of reality? All right, so have we gone forward just from the Utah teapot to being able to render everything in a computer science graduate student's apartment? Is that really what we're doing? All right, so let's go back to my weird acronym. Render everything you ever saw at Bob's house. All right, who's Bob? Who's Bob? This is a computer science graduate student. All right, so let's look at, in fact, the average computer science graduate student over the last 50 years. Let's be real. All right, frankly, just look at like the older professors in our field, right? These are all going to be white men, right? So everything at Bob's house, where Bob is a computer science graduate student, where, if we're being real, is a white guy. All right, here is another image from that Fast Company article saying, look, see this thing, this IKEA chair, this is computer generated. Wow. Does this look like a CS student's like chair in their room or what, right? So like how many of you have a piece of like IKEA furniture like in your apartment right now? Like, did you buy it when you're a grad student? Maybe you're still a grad student, right? But did you buy it when you're a grad student? Do you have friends who have like IKEA furniture in their house right now? I bet you do. All right. So it's kind of hard not to wonder if the same thing as the Utah teapot is happening right here. Like all these algorithms, they're just designed to render everything like in a computer science graduate student's housing. So this is the stuff from Bob's house. All right, so this theme, it actually extends past rendering and it informs lots of other algorithms at SIGGRAPH. This is my assertion. Right, so a few years ago, there was a SIGGRAPH paper written on arranging the furniture in your house. All right, so you just throw down a bunch of furniture and it'll come up with a good layout for the furniture in your house. All right, here's one of the main results from the paper. And I'm gonna ask you, all right, is this your house? Is this your house? Or is this the house of like a PhD student and like his roommates? Like, I'm pretty sure it is, right? Actually, to be honest, this looks like the house that I lived in when I was a PhD student, all the way down to like the weird yellowy couches that like just sort of came with the place. And if you sat down on it, like the springs are all messed up. Like it looks like that house. All right, we can get really super on the nose with it. Actually, there's lots of graphics papers on like literally generating instructions to assemble IKEA-like furniture. All right, so we have a paper from 2014 for assembling IKEA-like furniture. So the stuff that was literally at hand when people came up with these algorithms. We can even say it like more on the nose. There's actually other SIGGRAPH papers that talk about generating literally IKEA furniture. All right, you can see it in the label down there. Look, 2 IKEA table models, Mehmet and Norden. All right. Where did they get the idea to write a paper about this sort of thing? They probably looked around themselves and they said, yeah, that thing in my room. Yeah, let's do that. And there's literally papers on reproducing the look of the knots of wood in IKEA furniture. So high-end furniture, the type of imperfections we see in the wood here, they would actually throw those pieces of wood away, right? Because these knots that we see here, they're considered ugly and structurally compromising. Not IKEA though. IKEA actually would use wood that actually has these kinds of knots in them. And that's why the furniture is cheaper, all right? And that's actually why grad students can afford to purchase them. Okay, so race, maybe we're just rendering everything we ever saw at Bob's house. Let's take a tour of Bob's house. All right, so here's a room at Bob's house. Here is the kind of spare desk that he did all of his work at and the torch lamp. Then it's kind of sad, it's a rental, so he doesn't have anything on the walls. All right, here's Bob's bathroom. All right, here's the computer that Bob wrote his dissertation on. Here is the coffee travel mug that Bob drank the coffee out of as he was writing his dissertation. All right, these are all algorithms for rendering these sorts of features. All right, here's a kettle that Bob used to boil the coffee that he's drinking out of his coffee mug. And here's a close-up shot of the door of Bob's car in Bob's driveway. All right, other papers in computer graphics. Here's a rendering of Bob's kitchen, which really, really suspiciously looks like the kitchen from the IKEA catalog. All right, here is a shot from Bob's living room on a dusty day. And I'm going to show another shot from the IKEA catalog, just to note how similar these things are. So you see like the little paper sphere lamp, like in the middle of the room, hanging from the middle of the ceiling. That's going to be in the next shot too. All right, so this is on a dusty day. Here's on a clearer day. You can see, yeah, there's a little paper orb lamp hanging in the middle of the room. All right, last example. Here is Bob's home studio. This is actually PBRT. This is like the Bible for physics-based rendering in the computer graphics community. This is a great book, by the way. I use it all the time. But let's look at the actual cover rendering. If you go on the website, you can see a wider rendering of the same scene. It's this studio. All right, this is Bob's studio. Okay, let's look at another shot from the IKEA catalog. All right, here's a shot from the IKEA catalog. It sure looks similar, doesn't it? In fact, I'm going to call out stuff that's super similar. All right, so the lighting is coming in from the right, and then you can see a little floor mat on the lower left, and then like a chair behind it. Right, so actually it's exactly the same in this. So the lighting is coming in for the right. There's a floor mat on the left with a chair positioned above it, and even the lamps look about the same. So again, one more time, back and forth. All right, here is IKEA. Here is a computer graphics rendering, and here's IKEA again. All right. So it really sure looks like we're just rendering all the stuff at Bob's IKEA-filled house. And it seems like I'm trying to like beat up on a bunch of SIGGRAPH papers here. And honestly, I'm not. I really do think those papers are worthwhile. They succeed at the problems that they set out to do. Rather, what I'm showing is that what Gabouret said, and he couldn't say it in with this level of evidence because he's not a computer graphics researcher. What he said, I think it actually is true. All right, so reality is unequally distributed in any given rendering. All right, so some of the stuff that we see in computer graphics, it's just pure more real looking than other stuff. And this is because researchers, for whatever reason, they've invested just more effort into getting it to look right. So these algorithms are really good at depicting whatever objects were at hand when researchers were writing their PhD dissertations, and that happens to be the stuff that was in the houses of grad students or professors at Utah or Stanford or Cornell. So I got my BS at Cornell, so I'm implicated in this too. That the stuff that was in your apartments, that's just going to look more real than everything else. So this is all just the stuff from Bob's house. All right, we can go back to this image. So again, I'm obsessed with the dirt by the side of the road here, right? So the dirt by the side of the road on the highway, that is definitely something that is not at Bob's house. So it's not that surprising that it doesn't look all that great. In fact, this is sort of like the stereotype of CS students, right? Like we all just stay in dark rooms and program. We don't get outside, right? Get outside, CS grad student, get some sunshine on your face, get some dirt under your nails. You're losing all your vitamin D, that sort of thing. This is just the stereotype that's sort of enacted in the fact that the dirt doesn't look all that great in this rendering. Instead, what do? We spend all of our time in like offices and coffee shops, filled with cheap furniture, and surprise, surprise, the cheap furniture, that's what these algorithms are really good at rendering. So reality concentrates around those features instead. All right, one last rewind to Utah from the 1970s. Unfortunately, I've saved the ugliest version of this thesis for last. All right, let's go back to this quote from before. So these were the objects that were ready to hand as researchers began their work. All right, the ugliest version of this. All right, here's something else that was being digitized back in the 1980s. All right, this is a plaster cast of Ed Catmull's hand from 1972. All right, again, I know this is a vision conference. If you don't know who Ed Catmull is, this was Ivan Sutherland's PhD student back at the time. He then went on to found Pixar. He went and made all the Toy Story movies, and he himself won the Turing Award in 2020. All right, so he is literally using here what is ready at hand, though. His actual hand, right? His actual hand. So now we're just rendering the stuff from Ed's house, and certainly Ed's hand counts as something that's in Ed's house. This actually ended up being like the first piece of 3D computer graphics to ever show up in a movie. So this shows up 2 years later in Future World. Here, I'll play the sequence. This actually is the same digitization. This is the sequel to the movie Westworld. And if you're thinking to yourself, hey, wasn't there like an HBO series called Westworld a few years ago? Yep. It's actually a reboot. All right, so Westworld, the HBO series, was a reboot of this 1970s movie. Same story. All right, this isn't the only example of rendering what's literally at hand. So we can go back to the French emigre Henry Garreau in Utah in the 70s. All right, here's his wife Sylvie Garreau. Her face is being digitized, and we're not rendering everything we ever saw. We're rendering everything at Henry's house, including his wife Sylvie. All right, same thing with another grad student, Fred Park. This is Vicky Park, his wife. Also, Fred Park was a University of Utah grad student, would go on to become a very well-known graphics researcher. All right, this is the stuff at Fred's house. I'm gonna just vocalize this. I'm not gonna dig too much into it. There's a very unpleasant theme here, of course, of we're literally objectifying women here, right? We're literally turning them into objects of study. I will acknowledge that that is what's going on here. It would take like a whole talk to actually do justice to this topic, so I'm not going to try to do it here. But Gabriel does talk about this in his book, though. So if you're interested in sort of the ramifications of this, I encourage you to read his book. All right, so back to the hand. This is not photorealistic, right? This is like a far cry from photorealistic. So you're gonna have to wait like a few decades before this looks more photorealistic. But let's go to like 2014. Here's a paper with a hand rendering. It's pretty good, right? Pretty convincing hand rendering. So success. All right, same thing with Sylvie Garreau's face. We're gonna have to wait a few decades before this looks better. But 2015, this is a rendering. It's pretty good, right? Credit where credit is due. This is a pretty good face. All right, I said I saved the unpleasant part for last year. Okay, these are all white people, right? So when we say that we have generated like realistic humans, what we actually mean is that we've like depicted white skin accurately. So we have Ed Catmull's hand, we have Garreau's face, we have Park's face. This is all white skin, right? So when people are trying to like traverse the chasm of realistic humans, this is the goal that they have in mind. They have the images on the bottom, but they have the mental images along the top. All right, the implicit statement of what aspects of reality should receive research attention. This is encoded in the objects that were being studied. All right, here's another image. This is from Wallace Koenig Greenberg's 1987 SIGGRAPH paper. The paper is a two-pass solution to the rendering equation, a synthesis of ray tracing and radiosity methods. So this is one of the key renderings from the paper. It's called Dutch Interior. This is actually a direct reference. I believe they say this in the paper. This is a direct reference to a Vermeer painting. This is called The Music Lesson. All right, let's look at these two next to each other. And again, I'm not necessarily trying to like just beat up on these papers. Credit goes where credit is due. All right, on the left, what were they trying to do? They were trying to get this very subtle light that spreads across the wall to look correct, and they succeeded. Right, it's beautiful. Like it actually does this very closely to the original Vermeer painting. But let's look at other places in the image. All right, what's missing? All right, on the right, we have like a vase and like a tablecloth, and there's like a cello, it looks like, on the floor. What's really missing though, it's the humans, right? So the white people are missing from this image. So actually this absence of white people from computer graphics research, this was codified for an entire generation of researchers, including me. So this is the cover of the standard textbook when I was an undergrad. This is Foley, Van Dam, Feiner, and Hughes, all right, Computer Graphics Principles and Practice. So this showed you from the moment you walked into a computer graphics class, what computer graphics could do and where there was still room for improvement, all right? So, and the room for improvement was we can't do virtual humans that well yet. So not just any humans, white humans. Subtle interiors of lighting along interiors, we can do that pretty well. All right, but this is the humans that it was actually referencing, right? So it's a Vermeer painting. It was referencing the humans in Vermeer painting. So girl with a pearl earring, girl with a red hat, the white humans that you see here. And we can see the effects of this in computer graphics research over a 20-year span. Right, so we get decades of work that's hyper-focused on capturing the look of white skin. Right, here's a tableau of skin rendering papers over the last 20 years. Look, it's all white people. It's not like I left out the black person that was in all these renderings. It's just not in these papers. All right, so the algorithms for depicting human skin here, they have all focused on subsurface scattering. This is the piece of physics that's most characteristic of white skin. And to be frank, it's the most characteristic of a white person you would see in a Vermeer painting. And this is not a coincidence. A generation of computer graphics researchers, they were pointed in this direction the moment they walked into their first computer graphics class, right? Before they even opened the book, it was actually on the cover of the book. Okay, I promised you I'm going to bring it back around to synthetic data at the end. So let's go back to synthetic data. So one of the prime motivations for using synthetic data is that real world data can have biases that are hidden in the data collection process. So it did not sample reality uniformly, if that's even possible, all right? But it could have these sorts of biases. So instead, the motivation is let's use computer graphics algorithms. The assumption is that this will sample reality uniformly, but actually, I think it has the same problem, right? So if we look at computer graphics papers themselves as like individual samples in this space, you're going to see that certain aspects of reality are grossly oversampled, right? So there's lots of papers with lots of car renderings and planes and military vehicles and white people in them. So there are some dark-skinned people in this shot. So it seems like it can at least do something passable here. But what are the ramifications for their appearance if reality is unequally distributed in these algorithms? All right, so we can compare these to images of black skin from movies. And if you look from the left to the right, ones on the left, they look weirdly diffuse. It's like somebody put tons of pancake makeup on their faces. Where are the shiny little highlights that are everywhere on the right? All right, it's quite clear that somebody applied technology that was designed to give everybody like this Vermeer-like glow to the people on the left. Okay, let's look at one last video clip of our reality being unequally distributed. This is a video clip from the opening of the movie from last year, The Woman King. Right. So just as setup, Viola Davis is General Naniska. She is the leader of an all-female group of warriors called the Agoge in the African kingdom of Dahomey in 1823. So what she's doing here is she's leading a raid against a bunch of slavers who have kidnapped people, and we're going to sell them into slavery. So there's no CGI in this shot. What I want you to pay attention to is that the warriors, they all oil themselves up before combat so that if somebody from the other side tries to grab them, their hand will slip right off, right? There's going to be a very characteristic shine to all of their skin. That's what I want you to look at in this shot. All right, this last frame, this is extremely carefully composed, right? This is dark skin at night on a dark background. And yet this is totally legible because all of the reflections on their skin were so carefully choreographed in this shot. Again, this is not a CGI rendering. The question is, for CGI algorithms, does reality cluster around this sort of reflection? So here are some close-ups of Viola Davis as General Naniska, and here's two of her main warriors. All right, again, let's look at those virtual humans from before. Where are the specular highlights, right? Is reality really equally distributed in these algorithms? So synthetic data, it gives you an illusion, I think, that you're controlling distribution of your training data. So the way that reality is distributed in this data, it's not uniform. So assuming that these algorithms are somehow objective, I think that would be a mistake. So how will all this play out? If people keep using this as synthetic data, I think it's going to play out just one news article at a time. We're going to see systems trained on this data just fail in really spectacular ways. And it's going to be really insidious, actually. So you're not going to even be able to say like, oh no, the training set contains too many samples of X and not enough samples of Y, and therefore we need to rebalance the training set. That's not going to be what happens. What's going to happen is the error is going to appear at a subsample level. So part of each sample is going to be more real than others. So it's going to have spatially varying subsample error, which sounds really horrible. Because I think it actually is. All right, so it's going to be incredibly difficult to dig out this error once it's entrenched in these algorithms. So if you have to use synthetic training data for your algorithm, I think you should take some precautions. So one, you should be real about what features you're actually looking for in your data to begin with. And if you're going to use synthetic training data, go back and see if there's an actual SIGGRAPH paper that's actually written on the feature that you're looking for. All right. Not only that, make sure that SIGGRAPH paper that you found actually does experimental validations against real world measurements. So what you're going to see is that even though these papers have been written for the last 50 years, there's actually like a really, really slim number of the papers that actually go the full pipeline to actual experimental validation. All right. Instead, what you're going to see is synthetic data. It's actually highly clustered. But if you want to do your science right, it has to have been validated some way, right? So this is what you're going to have to do if you want to do your science right. All right, that's what I'm going to leave you all with today. Thanks to everyone for listening, and I'd be happy to take some questions now.
Thank you. That was such an enjoyable talk with some real world impact and really lack of real world representation, I would say. So anyone on the Zoom call, if you had questions during the presentation, please repeat them in the chat so that I can repeat them here. And everyone in the room, please walk up to the microphone in the middle of the room so that we can have your questions. And apologies from both of the audiences that my voice is giving up today because of my allergies. Okay, we have a question in the room.
Hi, this is Pavan Furaga from Arizona State University. I really enjoyed your talk. I also hang out with a bunch of artists and filmmakers. I'm from the School of Arts, Media Engineering. Here's a question. Not considering myself an art historian, but since the invention of photography, if you go back to just art, not film, just basic art, realism was considered no longer particularly interesting since realism just meant capturing a picture. And there's always been this balance between what they may call mimesis versus abstraction, and that's where the interesting art gets made. So in film, it looks like the direction is still very much towards realism. The big blockbusters are all about realism. Do you see any change happening towards abstraction and magic realism in that way in film?
Oh, very interesting. Oh, wow, this is really left field. Let's see. Okay, wait, should I be repeating the question or typing it into the chat box? Okay, all right,
No,
so
I think everyone can hear it. I think, yes.
Okay, let's see. So, to be real, like, I mean, from like all the animation studios, it's like, yeah, so people are still going to try to make the next Toy Story. So there's like a very small delta that you can sort of drift away from before it becomes too weird for general consumption. That being said, I don't work there anymore, so I can say this, right? Let's look at the box office this weekend, right? It's like Elemental bombed while the Spider-Verse movie actually still is doing extremely well. So the Spider-Verse movie, like, this is highly stylized, right? So there actually is at least some hunger to like, can we get away from like you said, like just sort of this boring mimesis where the sort of the storytelling space has been oversampled over the last few decades or so, and something that's a little bit more abstract. I think there is some hunger for this. You're gonna have to overcome some industrial inertia for that sort of thing, though. So like even at Pixar, when I was there, the first Spider-Verse movie came out, and people were like, "Oh my gosh, this is amazing! Why didn't we make this movie?" Right? People loved that kind of abstraction. It would be great if those kind of tools were developed so that you could make some more beautiful movies like this. We're the academics, right? Let's do it. We should be the ones that are actually doing it. I think that's a great idea. And then maybe we'll just like stop thinking about the synthetic data in this sense. It's like, no, look, it's an abstraction. You can see the abstraction. Just look at all these cool new algorithms that are just abstract now.
Questions in the room? In the Zoom? I have one question actually. By the way, when I look at this, it means I'm looking at the participants. When I look at this, it's like I'm looking at the room. Anyways, I look at the participants. reality is not equally sampled when we look at from the rendering perspective, modeling perspective, like scene composition, object modeling, etc. But if we go a little bit away from traditional modeling and traditional maybe generation and look at the current like deep generative models, diffusion models, etc. Do you think we are moving towards more equal distribution of world data in terms of images, and hopefully because all of these like X to 3D models are being built, like even in 3D, we will have better real world representations and better, more diverse representations of not just Bob's house, but anything we see, not even houses, but like anything in nature, etc.
So yeah, and I can't pretend to be versed in the entire field, but let's see. One of the things that I considered discussing in this talk, but it didn't quite fit, was hair. So the thing about extremely curly hair is that geometrically it does seem to live on the opposite end of a certain continuum of hair that has been very, very undersampled. So you look at like all the hair generation papers, from like CVPR and stuff like that. Credit where credit is due. People are more honest about this now. It's like, yeah, we do lots of straight hair, so we segmented it out to straight hair. Look, it matches the photo pretty well. And we're going to show you a failure case, and the failure case almost invariably is on extremely curly hair. So afro textured hair. This is a highly raced feature, right? So this is most characteristic of Black people. So this geometric feature seems to be very poorly sampled. If someone could come up with an amazing, deep learning based algorithm that actually captures this geometry in some amazing way, that would be awesome. I would love to see that, actually. I don't know how this would happen though, because maybe you can get like point clouds or something like that, and then you can like guess on the interior of the hair, a little bit better. But it does seem like we still use first order methods for geometric modeling. So like, the line segment or something like that, or like a cylinder, it seems to be still the first order the primitive that people actually use. Whereas, if you're actually going to do highly curled hair, the base primitive, it does seem like it should be like a helix or something like that. It should be some curve based primitive instead. So maybe that's what the deep learning will actually give us. It's like, oh, so all these higher order geometric methods, it's like these are really hard for people to use before, but now these quadratic fits or something like that, it's actually really easy to do. Or somebody found something super slick to actually do this. If that happened, that'd be awesome. But that being said, I haven't actually seen it yet.
Maybe the next skeleton challenge is actually extracting hair curves from 3D data. Why not? We have another question on the chat, and I'm reading it for the participants in the room. So Celia actually asks that, thank you for the amazing talk. Playing a bit of devil's advocate, sometimes when we run algorithms on objects that are lying around the house, it's our way of saying, look, it runs on any object, and ensuring that the results are not cherry-picked. As the set of graduate students becomes more and more diverse, and to be fair, many results from this past 10 years that you showed are by non-white male grad student first authors. Yeah, sure. Is it really a bad thing that we test on what we have at home?
That is an excellent point. That's an excellent point. So it's like, okay, so if we diversify the grad student population, then Bob's house actually will be everybody's house, right? And yeah, it would be great if that actually happened. Sorry, I'm going to take a shot at deep learning now. All right, I'm going to take a shot at you guys. So the synthetic training pipeline, though, it works against this, right? It's like, okay, let's assume that the existing algorithms are already good at everybody's house, and then let's push that down a layer in the stack, right? So we'll generate the training data based on that, and then we'll generate another algorithm on top of that. If that is what happens, then it's going to be like, yeah, well, so finally Bob's house represents everybody, but now we're not even developing these foundational algorithms anymore. They got pushed lower down in the stack. It's like not really like fashionable to work on these foundational algorithms anymore. Accelerating them using a deep learning method, that is where you're going to get your faculty position from. That could be what happens. So okay, maybe that's why it's important to ask this question. It's like, okay, everyone, deep learning is great. We can get all these really interesting results out of it, but there's still tons of work to be done on foundational algorithms that actually feed these deep learning methods. We can't give up on those because if we do, then we're going to just re-entrench the stuff that happened back in the 1970s.
I absolutely agree to that. Okay, any other questions in the room or in the Zoom? I don't see on the Zoom. There's thanks and there's also a lot of comments. Anything else? If not, we thank you again a lot. This was a wonderful talk, a super nice different perspective. I love SIGGRAPH jobs. I love the economics perspective. I love seeing the books of junior, so thank you for being here. And let's give another applause. Okay. So we will continue with our next session, which is the second presentation of the workshop, which is called GAMSIM, Unsupervised Generic Garment Simulator.
And the presentation is also pre-recorded, but I guess the authors should be here for questions afterwards.
Hello everyone, I'm Lokinder. Hello everyone, I am Lokinder. I am a research scientist at TCS Research. I am presenting my work on unsupervised generic garment simulator. We call our method GenSim. It is an unsupervised generic neural garment simulator. It can simulate garments of arbitrary types, sizes, and topologies on arbitrary body shapes and poses. As it is shown in the figure, GenSim takes garment draped on the person in a canonical pose and the target pose as an input and predicts the deformed garment on the target pose. The textured output and the overlaid output shows that the predicted garment respects the underlying body shape and deforms accordingly. As you can see here, you can see here. The motivation of our work came from the limitations of the earlier works. We can categorize the earlier work into supervised, self-supervised, and unsupervised categories. These methods can handle different kind of variations during inference. For example, TaylorNet can handle only the variation in the body shape and poses, as you can see here. It can handle garment on which it is trained. For different garment, it needs to train a new model. Similarly, there are other methods such as garnet, deep draper, enclothe, etc. They also require retraining for every new garment. Method like DPSD and GARSIM, they can handle different type of garments, body shapes, and poses during inference. However, they require labeled data to train the model, which is often computationally expensive. Snug is a self-supervised method that doesn't require labeled data, but it is specific to a particular garment. Hence, it requires retraining for a new garment. Similarly, PBNS is an unsupervised method that can handle only variable poses. This is also a garment and human body specific model. Like other, which were only the garment specific models, PBNS is also specific to a garment and human body pair. Our method can handle variations in body shapes, poses, garment types, and topologies, and it can train using unsupervised losses, and it doesn't require any kind of label data. So our contributions here are a generic method for unsupervised garment simulation. GenSim can be trained simultaneously for multiple types of garments of varying sizes and topology and bodies of different shapes and poses. It generalizes on unseen garments of different types and sizes, along with different body shapes and poses. We present a novel motion-aware ARP garment deformation method that roughly aligns the template garment on the target pose. We also propose a physics enforcing network that corrects the output of the motion-aware ARP module to make the deformation physically plausible. Next, I will show an overview of GenSim. GenSim is a two-step framework where step 1 is a body motion aware ARP garment deformation, and step 2 is physics enforcing network. Step 1 takes garment draped on the canonical body pose and the target body pose to deform garment and roughly align it onto the top of target pose, considering the underlying body motion with respect to the canonical body pose. So this deformation is based on how a person moves from a canonical body pose to target body pose. Step 2 is a physics enforcing network that further corrects the step 1 deformed garment and make it physically consistent. In this step, we first create a encoded latent garment graph where nodes corresponds to the vertices of the garment mesh and edges are the mesh edges. Important information here like garment and the underlying body geometry and its motion. These are encoded in the node features, and edge feature encodes the relative location of garment edge vertices. The encoded garment graph is passed into a meshes passing network, which updates the node and edge feature in every pass. After the total L passes, the latent node features are passed to the decoder, which predicts the per vertex displacements. The displacements are then added to the step 1 motion aware ARP deformed garment to predict the physically correct output. So as you can see here, this G plus delta is what is the final predicted garment. Here this delta is per vertex displacement, which we have added to the ARP deformed garment G. So next we see each of these modules or these steps in detail. So first one is body motion aware ARP garment deformation. So the traditional ARP method cannot be applicable in our case because of two major reasons. First, traditional ARP method require a set of handle vertices which are unknown in this case and can be different for different target body pose. The second is the articulated human body under the garment act as an obstacle while deforming non-handle vertices. So these two are the main challenges which will basically make it difficult to directly apply traditional ARP method in our case. So we propose two solutions for these two challenges. One, we first automate the process of identifying the garment handle vertices, and this is conditioned on the underlying body motion. So we consider the underlying body motion, which is the motion with respect to the canonical pose, and identify the garment handle vertices in a completely automated fashion. Second, we propose a motion-aware multi-step approach with collision handling. This will consider the underlying body as an obstacle. We compute the final location of the handle vertices and move the handle vertices to their final location in multiple steps while handling the collision at each step. So the final motion aware ARP deformed garment is free from collision and roughly aligned on the target body pose. So here on the right hand side in this diagram, we have shown how to compute the we have shown basically how we compute the final location of the handle garment vertices. So the process of finding this final location of handle vertices is shown in this figure, and we have shown a cross section of garment around two legs. You can see these two are the legs, and this pink contour is representing the garment. Here the garment is, for example, skirt. So in figure A, the magenta vertices are the handle vertices, and in green are the non-handle vertices. So these handle vertices are automatically estimated. So assuming there is only one leg which is moved, for example, this gray leg is the new position of this particular leg. The moved leg are shown this moved leg is shown in the gray. The location of the handle vertices are computed by moving them along the direction of motion with a magnitude which is the length of a vector di and subtracted by q. So the detail of all these symbols and like the computation is in the main paper. So in the interest of time, so I'm now discussing the algorithm 1 and algorithm 2, which is used for computing the handle vertices and moving and deforming the garment based on the underlying body motion. So why body aware motion ARP? So an alternate to get the initial rough alignment is to use linear blend scanning approach. So I mean, we could have used LBS or linear blend scanning based approach to get the initial rough aligned garment on top of target body pose. Now, so what happens in the linear blend scanning approach? We basically borrow the weight, the scanning weight for each garment vertex from the closest body vertex. This strategy generally works well for a body hugging garment, but drastically fails for loose garment. As we can see in the figure, observe the weird elongation of edges, while on the other hand, our proposed solution deformed garment based on the underlying motion and doesn't distort the edges too much. As you can see, we have shown the zoomed version of this particular region here. The edges are extremely elongated, but in our case, you can see the mesh edges are not distorted and they are keeping the garment quality intact. Okay, so next is the pen network. The encoded garment graph consists of the latent node features and edge features. The latent node features encodes the body and garment geometric features, this F gar and F body. The relative position of garment vertices with respect to the body, as you can see here, this U. The relative position of ARP deformed garment with respect to the target body, this V. Pin verticid indicator P, body motion vector D, and the mass of the garment vertices M. So all of these information are concatenated and passed to the node feature encoder, and this feature encoder basically gives for every node of a latent feature which is embedded into the respective node in this particular garment graph. Now latent edge features, basically these are encoding the relative position of garment and vertices, which is E and EARP. So here we encode the relative position of garment and vertices for both the template garment and the ARP deformed garment, which is EARP. So now we have this encoded garment graph where we have encoded latent node features and edge features. Now this garment graph is encoded garment graph is passed into the message passing neural network block. So the decoder takes the processed encoded garment graph and basically it takes the processed node features and pass it to the displacement decoder. The displacement decoder predicts per vertex direction and the magnitude of the displacement. Gpred is the predicted final predicted garment. The novel formulation of direction of displacement ensure that there is no collision with respect to the local body surface. Now consider figure here A and B, where garment vertex and its closest body vertex are shown in magenta and black respectively. Here, magenta and black respectively. And N hat is the body vertex unit normal. The direction D can be in the black gradient region, like this one, this half space in figure A, which is the half space created by the plane, which is the blue. So this line is the plane, and slightly from a perspective view, we have shown this blue plane here also. So in B or figure B, the orthogonal to the unit normal N hat and the vector D can be obtained as a convex combination of N and B. So now suppose this vector B has three coefficient B1, B2, B3. So the decoder essentially predicts the first two coefficient of vector B, which are basically B1 and B2, and a convex combination factor rho. So the magnitude of displacement omega for each of garment vertex is also predicted by the decoder. The third coefficient B3 can be estimated from the predicted B1 and B2. And so we get the B1, B2, B3 all for the vector B. Rho we have already predicted. and this D vector, the direction vector, is constructed in this manner. So please refer to the main paper for the detailed formulation of this particular step. Now, next we discuss the training losses. To train the GenSim, we employ various unsupervised losses. We propose a restraint energy loss that restrict edges to deform significantly, where mu and sigma fabric are the mean and the standard deviation of the edge lengths from the respective edge length in the template garment. So the bending energy restrict the bending of neighboring faces. The pin vertices loss restrict garment to fall down. The list of pin vertices are generally provided by the designers, but can also be automatically estimated by using the semantic of the underlying body. Potential energy apply force on the garment due to gravity. So this is the force which will pull down garment due to gravitational force. Mesh smoothness loss basically tries to maintain the surface quality, and the collision penalty loss restricts the garment to collide with the underlying body. So the total loss is the weighted sum of all these losses, which we use to train the GenSim in a end-to-end fashion. So we tested our method on Clo3 data set. We take a subset of Clo3 data set. Basically, we took the skirts and tops of the Clo3 data set. We trained two model, where one is the supervised L2 loss with the smoothness and collision loss. Other is the unsupervised physics, where physics losses, which we have discussed just in the previous slide. So we can see unsupervised version gives better result, and you can see the error in the edge length are less in the unsupervised physical losses. Smoothness quality, or the quality of a deformed garment surface, is better, and the collision is also significantly lower in the proposed method, where unsupervised physics losses are the losses basically which we proposed. Yeah. Rendering of some of the test samples are shown below. We can see GenSim is able to predict garment deformation on arbitrary body poses and shapes. And you can observe here the garments are also of different types and sizes. So our method, which is a single trained model, can handle all these variations in the body and the garment types and sizes. We further compare our method with DPSD and PBNS. Now, it is evident that DPSD suffers collision and PBNS also suffers collision, along with artifacts in the front of the garment, while ours gave a collision-free realistic garment deformation. Right? You can observe collision here. You can observe this weird artifacts in PBNS. Right? This collision here, this artifacts here. So these artifacts are very common in PBNS. Right? You can see here. So since PBNS is the closest method to ours, we further compare it on some different template garments. So now you can see here also the artifact is very much evident here in all different template garments. Right. So this V-shaped squeezing artifact between leg is prominent in all the output of PBNS. So this issue is also mentioned by the author in their paper, especially in the skirts. Although author claims that this issue is resolved to somewhat, but we observe the same artifact, especially in the long skirts. So we trained their officially released PBNS code following the protocol mentioned in their paper. So yeah. So and now you can also see in GenSim, our method doesn't have this kind of artifact and can be seen a more realistic natural garment deformation of loose garments, right? Loose skirts here. So to quantify the level of distortion due to these artifacts, we compute the Laplacian of all these garments, and you can see the lower is better. So our method is giving lower Laplacian value. So our method generalizes well to unseen type of garments. These garment were not present in the training set. You can see this shirt, this pant, this dress, this short, all of these were not available in the training set, but still our method is able to predict accurate geometric deformations, and also you can see textured garment are also showing the quality of the rendering. Okay, so we compared our method with video call method. This is a method from CVPR 2021. So we note that video call method is trained for this particular dress template, while the GenSim never seen this template during training. But still you can see that folds due to motion around waist and leg are there in our case, and also in that case. So here we can say that our method generalizes to unseen garment and competing with the methods which are specifically trained for those garments. Okay, so we tested our method on a random YouTube video, and for that we extract 3D human from these frames, that is SMPL model for all the persons in the video, and drape with different clothings. So you can see these persons are draped with different clothing and rendered on top of the their positions in the frame. So we performed some ablation experiments and ablation experiment on the loss terms. So on the left hand side, we trained GenSim without pin loss, and we can observe garment fall down. We also trained without restraint loss, but with the pin and the potential energy loss. We can see garment fall down, but at the same time stick around the pin vertices. So the version with the potential energy loss, pin loss, and the restraint energy gives better prediction, as you can see here. And this is the one which is very close to the ground truth garment deformation. In summary, we presented an unsupervised and generic garment simulator that can simultaneously be trained for multiple types of garments and generalized to unseen types of garments of varying sizes and topologies. We have also presented a novel motion-aware ARP garment deformation method for rough alignment of template garment on the target body pose while avoiding the local collisions with the body. We have also presented a physics enforcing network that corrects the output of motion-aware ARP module to make the deformation physically plausible. We have left handling garment collisions and layer garments as a future work. Thank you.
Thank you very much for this very nice presentation. So we have the authors in the Zoom. Are there any questions from the audience or in the Zoom room? Otherwise, I have one or two questions that are a bit nasty, honestly, but perhaps somebody here has a nice question. Yeah.
Hi, nice work. I'm wondering, some of these examples, particularly this curve, looks like there is a bit of a dynamics, like the skirt is flying away. Is it just a due to static, I mean high stiffness, bending stiffness? I'm trying to parse why the skirt looks fly away in the silhouettes.
I saw the authors on Zoom before. Could you read the question in the Zoom room? Can you hear us on Zoom? Hello? Hello, can people in Zoom hear us?
Yeah, we can hear you. I can hear you.
So, did you hear the question that was asked? Yes, we can hear you. I don't know if we can hear the person who's writing.
It looks like the author has some issues answering back.
Okay, no problem. We can take it. That's fine.
let's give the author like a minute or so to fix the audio problems, and then we try again. Or yes, otherwise you will get the questions offline. Okay, sorry, we can't hear you, so we will skip the Q&A. There is now a coffee break, is that right? And post a session for half an hour, and then we will reconvene. 3:30 for our last oral presentation. That one will be in person, so it would be really great if all of you and some more people are back in person, and that we are not alone with the only person who's here to present in person for this workshop. Cool. Thank you very much, and see you later. Hello. Okay.
Hey, Bernard, you want some testing or?
I think it's working. I would
Okay.
just start the screen sharing if you don't mind. Do you have videos in your presentation? Okay, perfect. It's like you just switch here and then you see that's the last one, next one, yours. Perfect. Yeah, excellent.
Oh my God, too many animations. I did not expect that. Okay, but that's fine. Isn't there just in case? I mean, yeah, but anyhow,
Yeah.
And most student reviews are like there's one in the web there are it's not there where you pick up your batch or the niche where it's one found. That's where from this search, there's only one post there. Oh, it's just maybe next.
Welcome back, everyone. Can we get a small confirmation from the virtual participants that you can hear me? By saying hi or writing something to the chat or some action that you can, perfect, there was an action, so you can hear me. We have our only physical presentation today, and it will be given by Pawan Turaga, because the first author can't be here physically. And he's from the Arizona State University, and you can see the title here, and I'm very much looking forward to your presentation.
Thank you, Bernard. Thank you, everybody. I'm hopeful my first author Rajans is on Zoom. I'm not sure. I think he is there. But thank you so much for being here and to hear my work on improving shape awareness and interpretability in deep networks using geometric moments. The basic idea of our work comes from this motivation that, when we perceive objects in a picture, there's typically two types of cues that people pay attention to. One is texture cues, color cues, and the other is geometric cues. And by geometric cues, we mean things like shape. However, many years of research in deep learning have shown us that the architectures for deep learning, including things like convolutional neural nets, which is the backbone of many of the pipelines we have for perception now, are biased towards texture cues. And what do we mean by that? I'll talk to you in just one sec. The idea behind, so what is it that is different between color processing / texture processing versus shape processing? At a very high level, color, let me not even say color, texture is often about gradient information in local image patches. You look at simple things like, edges and gradients, and the distribution of those gradients often convey something about texture. Whereas shape is not a local property. The shape of an object cannot be defined in terms of a small 3x3 patch. It is something that is global. It is something that links together high frequency gradient information across a bigger field of view. Now, that aspect of being able to link high frequency content across bigger fields of view requires slightly different types of mathematical operations, which deep learning has not successfully been able to do. What are those types of operations? I'll mention that in a little bit. But in this situation, I'm just trying to make a case that when we say perceptual tasks, we mean everything from detection to classification to segmentation, even generative, GAN types of models. All of those, network architectures in our assessment are texture heavy. Here is an example of what we mean by texture heavy. At the bottom right of this panel, and this is even not our work, this is well documented in CVPR literature. The primary reference is down below, ICLR 2018. If you take a picture of an elephant and you pass it to one of the classification networks, highly likely it gets classified as an elephant. So on the bottom of each picture, you have the top 3 classes that are being detected as likely classes. If you give it a cat, sure, there is a cat class, and that is high probability. But if you paste elephant skin texture onto the cat shape, and then we ask the network to recognize what it is still highly confidently telling us that it is an elephant. Now, this type of effect has been documented again and again and again, and oftentimes the kinds of tricks that are recommended more training set, more augmentation, that sort of stuff, rather than attack the problem at its foundation, which is we don't really know how to encode shape awareness into deep networks, other than let's just hope it does it. Shape awareness is not easy because many of the people in this workshop will probably be familiar with this other body of work called shape analysis, which has a very rich history all the way back from the 60s, and some very influential papers have been written by mostly mathematicians on trying to define shape. And the language they use, the methods they use, the math they use is not the same type of stuff that we see in deep learning. For example, shape analysis is very broad, is very rich, and I will not even try to get into the most contemporary definitions of shape. I will mention 2 definitions, or maybe 1 definition, which is a good starting point. So this stuff that I'm going to talk about is from the 60s, and this is from a paper by MKU this was pre-PANI, this was like pre-CVPR. The citation is something in the transactions of information theory or something like that. This person, MKU, was trying to look at binary pictures, images which were pure black or pure white. So typically things like a picture that has been segmented out through diagonal subtraction, and what you have is an outline and a blob that is only shape and there is no color or texture information. How would you represent that information in a way that can be used for object recognition? That's the type of question MKU was asking back in the 60s. One of the approaches that who went after, but didn't quite clearly define it, was the notion of coming up with rotation, translation, and scale invariant descriptors of that binary picture. The key part was his attempt at coming up with rotation, translation, scale, invariant descriptors. And you can do that in a number of ways, right? I mean, in hindsight, you can come up with many descriptors that have rotation, translation, scale, invariance. But his approach was to take projections of that image, the binary image, onto a basis function set, which looks like a polynomial type basis function set. Which is written in that first equation. It's a double integral implemented as a double summation on digital images. Where the basis functions are of the type x to the power p, y to the power q, where x and y represent the coordinates of the pixel, and f of xy is the value at that pixel, typically it's 0 or 1, but there is also a grayscale version to the same idea. And NPQ is called the raw moment of order p plus q. The visualizations, the institutions we have as the zero order moment, p equals 0, q equals 0 is simply the average, value of the picture or the total value. If you do a division by the total number of pixels, you get the average. With p equals 1, q equals 1, you get the center of mass of a blob. With orders, you start looking at other things like center of inertia and moments of inertia and things like that sometimes have a very physical meaning. Mathematically, this doesn't have to stop at orders of 0, 1s, and 2s. This can go to any number of orders. And there's a lot of mathematical theory that says as p and q tend to infinity, the set of moments that result are a full information preserving set of descriptors of fxy. You can go back and forth from fxy to mpq as p and q tend to infinity. In some ways, this is sort of like frequency decomposition methods, but applied to the spatial, blob-like things. So there is a increasing order of complexity of shapes that you can explain with higher order moments. But I would not use the word frequency decomposition in a literal sense. It's only in this equivalence sense that you have very interesting types of polynomial functions that can describe very complicated shapes. And the more of them you have, the more interesting shapes you can describe. And that's the basis for Hughes' approach. The raw moments in and of themselves do not have a fine rotation, translation, scale invariance. I mean, clearly, if you shifted fxy to the right, the center of gravity would shift to the right. So there is no invariance in the raw moments. And Hughes' contribution was to take these raw moments and to come up with a set of descriptors, which are tabulated at the bottom. He came up with a set of 7 descriptors, which he was able to prove with rotation, translation, and scale invariant. It involved a bunch of engineering, really. I mean, you have to very carefully look at what's happening in these moments and do the right normalizations, the right centerings, and get rid of rotation, translation, scale effects. This was a very influential in shape analysis for a number of decades. And these 7 moments would be used very frequently for object classification experiments, and even some of the very early experiments in digit classification with NNIST pre-deep learning would use these 7 descriptors for binarized images of those digits. Even into the 80s and 90s, this was well used until other features started kicking in. Now, we wanted to start to work with this. But the one comment I made before we talk about what we actually do with this is, what does shape really mean? In the 80s, there was yet another influential paper by Bill Kendall, which sparked this mathematical field of shape analysis. And he basically defined shape of a bunch of landmarks, xy coordinates or xyz coordinates, as the information that remains after you have removed the effects of translation, rotation, scale. He defined it in that way. Very close to being what he was getting at in terms of invariant descriptors. But by framing the problem as information that remains after factoring out certain variables, gives rise to very interesting mathematical descriptions of shape spaces as non-Euclidean spaces. And you can think of the set of landmarks as a matrix that has been, and you can think of 2 landmarks as equivalent if there exists a rotation translation scale that transforms one to the other. And that's the type of language that gives rise to shape manifolds. And there's a lot of interesting differential geometric ways to treat shape manifolds under that interpretation. We are not going that far. We're starting with some of the oldest definitions of shape, which are in terms of simple descriptors. So what do we want to do with this? Now, the strength of deep learning is clearly in learning some of these operations that we might want to motivate from more basic considerations, like projections onto polynomial bases. And that's how we are trying to make a blending between geometric movements and deep learning. At the bottom right, you have this equation, which is we're trying to redo the notion of a movement from this very super specific polynomial type, x to the power p, y to the power q. We want to go beyond that and replace that with some general smooth functions that a neural network can learn to figure out on its own, but preserve the dot productness between that polynomial basis and the image function. Also, we want to allow this projection to happen on image features, which might have roughly, the same types of resolutions as the original image through feature maps and through channels that come in deep learning. So you need to implement an equation like this into a classification architecture where FPQ is not, it could be the image, but it could also be a feature channel from the image, and a P subscript PQ are learned basis functions. Here is an architecture that we came up with. It looks complicated, but we can break it into two halves, the upper half and the lower half in a way. So the top half is essentially nothing but a ResNet type architecture that does classification into K classes. On the bottom right is how we are proposing to treat the coordinate functions, the projection operations. And this is where I would like to go back to the comment earlier, which is that the operations that help you get shape descriptors, that help you get shape awareness are, in my opinion, fundamentally very different than convolutional operations. So we let the convolutional operations stay as is on the top half, get the texture descriptors, that texture bias comes from the top. But on the bottom, we want to make it biased towards shape. And the way we make it biased towards shape is to first get rid of color, texture. So the input in the bottom shape line is not the image, but it is a coordinate grid of the same size as the image. And what it's trying to do is transform the coordinate grid and these con blocks that come right after it. We're going to learn those projection functions, the polynomial type basis functions. We take a product here between the image feature and the polynomial basis function. And the goal is end to end, it will learn the right polynomial basis functions that are helpful for classification. One of the key things we add in further stackings of this, it would be awesome if this learned the right polynomial basis functions in one shot, that we played around with this architecture and we found that we have to introduce this interesting affine transformation layer to get that rotation, translation, scale invariance, but slightly more general and affine invariance. By forcing, so we have this other prediction layer that converts some of these operations into an affine transform matrix. That affine transformation hits the same coordinate grid, and the transform coordinate grid is once again passed through these polynomial basis functions. And we treat that as the feature for the next layer, and we keep repeating this. So one is we are treating coordinate basis functions or coordinate data fundamentally differently than pixel data. And we are introducing these affine transformation layers in an attempt to get the network to learn shape-like things, because for this to make sense, if you're going to hit the coordinate basis with affine transforms, it has to learn some affine invariant representations in the coordinate bases for all this to gel well. So these are some of the high-level design principles we are implementing in this architecture. And of course, I spoke about this. I will not repeat that. So yeah, there is a coordinate grid going on and lots of details about how this is implemented. How to visualize features. One of the interesting things is, this type of decomposition of features, this dot product between feature and coordinate basis can be inverted. Just like you can go back from an image to moments and moments to images, we can reconstruct features, which allows very quick visualization of what the network is learning. And I'll show you the strength of that very soon. So reconstruction is not difficult. It's just, once again, take the product between the feature channel and the basis function and multiply by the moment that was computed. So going back to a reconstructed version of the feature channel is not hard. I will show you some intuitive results first, the visualizations first, before I show you these things. So here's what is going on. Now, if you take the first row of pictures, standard set of pictures from ImageNet, and if you try to visualize the features right before the classification layer through our moment reconstruction approach, this is how the moments look like. This is what the features are looking like as we stack further and further layers of the geometric moment computation module. That's over successive endings of this layer, we find that the features are really indeed highlighting the outlines of this foreground object while suppressing a lot of the texture of the background. Now, this is, in my view, very different than what you get from contemporary deep learning architectures of the convolutional type. In the convolutional type of architecture, first of all, you can get visualizations of the convolutional operations, and they tend to look like Gamma filter jets of different types. So you know they're looking at gradients and edges. But there is very little anywhere along the way that shows us that it's learning to identify whole objects and or highlighting entire outlines of those objects. For example, here is a visualization through a technique known as GradCam and other feature visualizations for other architectures. Same thing, top row set of pictures, pass through a classification network. Second row is GradCam, which allows you to probe the network and ask what in this picture contributed to your decision as a means to interpret its functioning. And the GradCam visualizations are like this. They tend to locate the object fairly well, but the blobs that they generate are essentially like attention maps or saliency maps, and they really don't have any detailed shape information in them. All the blobs look more or less the same. With more recent architectures like VIT, Vision Transformers, and other big architectures, if you probe them and you visualize the features they're learning, they start looking more interesting, but they're still very much distracted by things in the background, and it's very hard for them to link things into coherent shapes. What we're able to do is, with a very small set of parameters added on, we are able to shift that bias from texture only and gradient only to shape very significantly with very little overhead in terms of parameters. So that was is very interesting. Does it actually help in classification problems? Does it improve performance? And our answer is yes. So here are examples of classification accuracies on CIFAR and ImageNet, and we see anywhere between 2 to 4 percentage point improvements at a very, very tiny overhead in additional parameters. We also find that it's actually more interesting when you. So we removed the ResNet pooling layers to do this comparison in the previous slide, and if you add the ResNet pooling layers, the result is even more compelling. We don't see the benefit of pooling layers when we add the geometric moment modules in. And pooling layers are interesting. Some people would say pooling by definition, even the word is telling you it's pooling. That's the operation that would pool all these independent activations into something coherent. And we find there is very little benefit in doing that if you can add this geometric moment of a parallel module. We also find that fine-tuning our approach on a new data set is very easy. If you have a classification network already trained, you only need to fine-tune the bottom half of the coordinate basis computation network, and that's very little parameters to tune, and it works really well. These are examples of fine-tuning of different architectures, and pre-trained on ImageNet, fine-tuned on CIFAR, and with very little fine-tuning, we can get very competing performance. Color distortion is another very common test that is recommended to check for. ImageNet C is this data set which has many prescribed distortions. We're looking at specific things like blur and fog, things that would otherwise obscure gradient information and shape information. And we find that even under those distortions, we do perform better than standard ResNet architectures. Slightly higher accuracy, significantly lower. It's called MCE, the classification error. So average classification error over a bunch of distortions at different levels. So we are way lower than ResNet. So all of these are promising results, and we find that some of the benefits also carry over to segmentation problems, where interestingly, shape is very obviously necessary in segmentation problems that your objects need to have the proper shape that adhere to the underlying picture. And here is an example. To take a very standard, backbone architecture in B-Lab V3+, and push forward the segmentation accuracy by pretty significant margins. On two scale, you're seeing, at least in one architecture, you're seeing 10 percentage point improvements. And yeah, so I think we're finding lots of impact on many different problems, including classification, segmentation, and detection. And we are very hopeful that this will change the way we deal with shape and texture. In the preview, we also have an extension of this work, which will be presented on Tuesday, tomorrow, at the Moon conference. We were also able to integrate this notion of shape awareness through geometric movements into a generative model through a polynomial type implicit neural model. Question number 195, if you show up tomorrow, I'll be there. And it's also a hard paper. So we were really surprised at how easy it was to also put this together with a generative model. And here are some very quick examples of what we can do in the generative space. Totally the images, that's baseline. We're able to get very high quality image quality metrics as is at a fraction of parameters. That's already there. But we're also seeing that we are seeing some kind of disentangling of shape and what we're calling style, but really texture. We're able to take two source pictures. So if you look at shape manipulation, the first panel, source A, source B, there are certain affine parameters, there are certain blocks in the bottom half of our region architecture, which are encoding shape explicitly and texture at higher levels. We're able to freeze the texture and only morph the shape, or freeze the shape and only morph the texture. So this is the type of stuff we're able to do very easily with our geometric movements work. Tomorrow, if you show up at my poster. So key takeaways, I think what we're really asking is to think about shape a little more carefully. And the way we fuse it with deep learning has to be fundamentally different than adding just, more layers. Or, one of the things that people say is, oh, if you just want to add shape like things, add a fourth channel, so RGB, and let the fourth channel be a positional encoding of the pixel coordinates. But still, even if you did that positional encoding, but if you're still passing it to a convolutional architecture, we're fundamentally not using the operations that are needed to promote shape awareness. And the coordinate data has to be processed in a different way. And this is one of those ways in which we're promising that. Thank you so much. Big shout out to my student, Raghavan Singh, whose brilliant idea all of this was. He's unfortunately not here because of these issues. And he's also in the job market. So if you're looking for someone to hire, great kid to have. Thank you so much. Any questions? Yeah.
Thank you very much for your interesting work. I guess that if I have understood correctly, the main idea was to define some basic functions which were based on the coordinates and combine them with the convolutional features. But as we know, these basic functions have some indicators P and Q and are sensitive to the location, and they are not invariant with rotation or to be transferred, like this kind of things. I guess that transformed layer was responsible to overcome this problem, isn't it? Is that
yes? So the first affine transformation, yes, we cannot guarantee that we would learn affine invariant basis functions. So we are in a way learning affine covariant things by forcing those affine transforms into the layers.
That transform layer was some kind of transformations, such as
let's take a look.
Or
so you need to say, let's go back. So this one truly transformed grid.
Yeah,
this was an affine transformation. So full affine.
affine transformations.
Yeah, so that would be rotation, translations, scale, but also oblique.
Okay,
things.
I have two problems. First, two questions. First, isn't it better to, instead of a coordinate grid, we just use a binarized grayscale channel of the grid and attach it to the image that we are going to run the convolution layer on.
So you're saying take RGB and then take the grayscale version of it?
Yeah, RGB with the plus layer, which is
With the
just
grayscale? I mean, I don't know if that would add or to promote shape bias because I mean when we say texture, it's not only color. It's like even grayscale has texture. Like any gradient information that exists in color will propagate to grayscale. So it will still have that texture bias coming through.
If you binarize it,
Right. If you binarized it, sure. Right. Okay. So we're saying not just make grayscale, make binarized it. Right. Possible, but we don't. Yeah. Binarization is not straightforward. Yes. Yeah. Yeah.
The other question, do you know any prior work that have used the coordinates to combine it and trying to combine it with the convolution?
With RGB? I mean, there's a lot of papers that there is no formal technique that they employ. I mean, for example, if you look at implicit models in and of themselves, like image encodings with implicit neural networks, they would always have a positional encoding, but it's written as part of either a sinusoidal, the XY going to some sinusoidal function. So there is that type of work. This is in that realm. So we are indeed encoding positional data, but not through simple functions like that, but more complex functions. Then this other thing, which is you just add the XY, take the XY. So you add two channels. So there is RGB and X comma Y, and you pass that in. That I would call that as an engineering hack. I mean, there's many papers you will find which would do that. But then the way you do XY has to be different than the way you do with RGB. If you just pass that into a 5x5 convolution layer, it might still do something, but the thing is XY behave very differently. They have wider dynamic ranges, and then it's it's fundamentally a different beast. Yeah. Thank you.
Hi, very cool presentation. I'm from the robotic world and definitely have used image moments to like hack things together in terms of finding.
Yeah. Right. Yeah.
Yeah. So I guess my question is, with this architecture, what order of moments are you able to approximate? So are you going up to the fifth, sixth moment? Yeah.
Right. So we use maybe 10 stackings of what is being referred to as geometric moment level 1, 2. So in actual experiments we show it goes up to level 10. So in some weak way, this would be 10th order moments, but it's not very directly like that. But I would have the order say, yeah, it's about 10th order. Yeah. Yeah.
Thank you.
Yeah.
Hey. Cool presentation. Just a couple of questions. First, like the f of x, y that you're interested in, is that like a high value over the grid?
Sure. I mean, it's a feature channel. I wouldn't interpret it as height value because that would imply it's all positive, but it's a feature channel. So it could be whatever it is. Yeah.
Like scale, wherever you want.
Yeah.
And the other question is like here are you specifically concentrating on global shape analysis? Could you have like a more patch-based like input to the architecture that could learn more surface level analysis? And like I guess you were talking about manifolds earlier, but
yeah. I mean, so there is no 3D shape analysis here at the moment.
From the 2D, like for what you do right now, that's more like a 2D, like the analysis of the underlying shape, right? It's a global thing.
It's a global shape descriptor, right? So the limitations are that. I mean, if you want to have an approach that can somehow be sensitive to, let's say, multiple instances of different shapes in the scene, yes, we don't do that. But I imagine that to get there, we would need a detection pipeline first. I mean, we would apply this separately on different windows which have been detected as interesting shapes. We haven't yet built that. But surface level is interesting. I mean, that would require us to go to one additional dimension. Again, the fact that we can do this in the implicit space in the GAN side, because a lot of the stuff, image to 3D level surface reconstruction is through implicit models at this point of time. It might give us the right hooks, but we haven't yet figured it out. Yeah.
Cool. Thank you so much.
Yeah. Thank you. Any other questions? Oh, let's look at Zoom if there are any questions. So nothing. Excellent. Very clear presentation. Yes.
Advertised your poster for tomorrow, but you didn't tell us in which session. Is it in the morning or in the afternoon?
It's the afternoon. I mean, I don't have the time slot, but the afternoon session. Yeah.
And is your code available? Can I just try it out on different data sets?
Sure. Yes. The GAN code is on papers with code. I can certainly do that. This code was, I mean, I can ask this room to put it up on GitHub. I think it's in some form to be put up. Yeah, absolutely. Yeah.
I had a student last year working on some, like, not related to this, but on the paper you motivated it on originally with the shape bias. And we were thinking about plenty of medical imaging applications that could heavily benefit from having a stronger shape bias.
Right.
So if you release the code, I bet with you that people will try it out in medical data.
I would love to do that. Yeah. I mean, that's the hope too. Many people in medical imaging do say that shape is probably sometimes the most dominant thing we have. It's not shape and texture, right? Yes, Nilka.
Hi, hello. This is hi, sorry. Okay, this is better. I have a question to you and to everyone in the room and in the Zoom. So can we actually use the geometric moments or shape moments or any of the traditional moments in a new Skeleton challenge track so that we have even more elaborate ways to learn them and use them in different tasks?
I mean, I'm going to say the easy answer, yes, but sure. I mean, I want to look at some of the more the details of the challenge because I never participated in them. But I would like to see, I mean, as long as you have XYZ coordinate data of some kind, moments become relevant. So absolutely, yeah.
That's great.
Yeah.
I see it to everyone to think about.
Yeah, thank you.
So I've got a question. Like, so one of your motivations here was getting rid of the texture bias, and another approach we'll take to do that is like topological data analysis. Have you done any comparisons between those two fields?
So great questions. I mean, I do dabble in TDA as well. How would I compare this with that? So the thing with TDA is the baseline pipelines in topological data analysis would require you to have binarization, right? You have to have the coordinates figured out first. In this case, we are not doing that. However, it's certainly an interesting thought. Like from that point on, like if once we have that final feature, I can imagine pushing that into a TDA pipeline after some binarization and having some features come from there. You know, we haven't tried to do that, but in other contexts where we actually have point cloud data, like clearly given to us as coordinates. But we've not been able to do that with image data because these are, but if you need like scalar TDA, if you mean, you know, the filtrations version of TDA.
Like the two versions.
Yeah.
Trying to put them together is also just trying to compare them and seeing
I
how
would-
they filter out this texture information.
I mean, I would say we haven't thought about TDA in this context, but we have thought about TDA in general. But I'm not to highlight it here and see it's there. Yeah. Thank you. Excellent. I think that's it. Thank you so much, folks. Appreciate it. Thank you.
So now we have to change the setup a little bit again. Sorry about that. And what do we do first, Ilke? Yep. And you just sent me the slides before, right? $7 minutes ago?
Yes.
Okay, perfect.
Yep.
You have videos? No, right? There's no video in it. Um, So the Zoom audience should see again slides. Please complain if that's not the case. And then you can take it away.
Yes, sure, yes. Zoom people, can you make a sound if you can see it?
Yes, we can see it.
Thanks, Anna. And hi, hello. I don't want to disturb your conversation, sorry. Sorry, that was a really good conversation going on in the room, so, okay. Well, welcome everyone. If you have been in one of the deep learning for geometric computing workshops before, you should be familiar with our Skeleton challenges. If you are not familiar, now we are going on and jumping into the challenges. So, a little bit of us about the history of Skeleton. In 2013, a wonderful group under AWM, Association of Women Mathematicians, the subgroup, sub-research network under that called Women in Shape, came together, and there were so many interests in skeletons. How do we extract skeletons? How do we traditionally find the median axis, etc. Some people with England came together in 2016, which in Trier, Germany, and now deep learning approaches were running, right? Like if you can imagine that from 2013 to 2016, deep learning was becoming part of our lives. Then in 2019, we joined forces of all of these different edges, let's say, different ends. And we had the first Skeleton challenge. Then in 2021, we came together back in Oaxaca, Mexico, sorry. And unfortunately, that was virtual because of COVID, but it was still a beautiful gathering. And you can see most of the wish people in the very first one, I mean, not first wish, but first of the committee here getting together in 2003 in the photo below. The organizers are actually pointed with yellow arrows. Okay, so as I mentioned in the beginning, like deep learning is erasing everything, analysis tasks such as recognition, detection, etc. But what about global shape understanding? What about just like the previous talk, like global shape understanding? Like, can we go beyond like associated colors and textures and understand the actual representation of the shape in 2D, 3D, etc.? Can we actually do shape decompositions and more? So this workshop focuses on geometric deep learning for shape understanding and bringing together mathematicians, computer scientists, computer vision, computer graphics, as we saw in the last keynote, right? All together to actually work on these public data sets and baselines and submit our collectively submit our results to global benchmarks by different approaches and organizing this workshop to spark new collaborations and ideas. And maybe one thing I want to mention is the collaboration session, open collaboration session right after this is actually a significant landmark of this workshop because many people from all around the world came together in that collaboration session and started new projects, like made super nice ideation sessions. If you look at the live streaming or recorded version of our previous workshops, you can see that like some of the seeds, some of the key ideas actually come from this workshop here. Okay, what are the tracks? I have been saying skeleton. So the first track is pixel skeleton, where we have binary shapes or shape silhouettes and binary skeletons. So it's actually basically can we shrink and find that skeleton of the silhouette. But we don't want to do it traditionally because traditional approaches already prove themselves in some domains. They already have limitations in other domains. There is always this like if there's boundary noise or the skeletons are overbranching or if there's pixelation or low resolution of silhouettes, etc. So can we actually have more robust deep learning-based architectures for global shape understanding? Second one is point skeleton. So for silhouettes, we have the image grid, we have the pixels, right? And can we actually do this in an unstructured domain, which is point clouds, which can have different sampling density, which can be flexible or not flexible against noise, which may be missing parts or which may have holes. Can we actually do skeleton extraction with these unstructured domains? The third one is still going back to the silhouettes, but can we extract parametric skeletons? And in this case, we are representing them with Bezier curves. If you were here for Theodore's keynote, he mentioned so many times about Bezier curves, which is one of the main modeling building blocks back in the solid modeling world. So can we actually extract these skeletons with Bezier curves so that they are more controllable, they are continuous representations, their editing is more easier than like just editing pixels, etc. Then lastly, we have image skeleton. So this came a little bit after than the original 3 tracks. This was our new 4th track back in a couple of years ago. And here we are taking the image, binary image world to RGB image world, and with foreground and background different. So it's not just the colored elephant, but elephant within its environment, and maybe there are multiple instances of the elephant, etc. So can we actually do skeleton extraction in these noisy real world examples? So how do we prepare the initial ground truth data is by applying interior bloom medial axis, PMA, which is points equidistant from boundary and distances. But of course, if we can already do it in a traditional way, then why we are trying to do it in a different way? So this suffers from robustness, and small perturbations on the boundary makes it branch a lot. And of course, the resolution, sampling, and parameterization is domain dependent. So if we are doing something in the point cloud domain versus parametric domain, it's actually changing. So the ground truth is actually done with a set dilation and inversion before the image so that we get rid of the branching. Then we have manual adjustment if closing changes. We have many selection of branches, manual of isolated skeleton. So we are trying to prepare this ground truth data set that is the beautiful, the most reasonable skeleton that we can extract from it. Now, for the first track, this is the shapes come from combination of 4 different shape reports. And they are all represented in 256 by 256 pixels. We provide shape images and skeleton images, as you see here. And as I said in the beginning, it's not only like some of our samples are by like animals and living things, but it's actually shaped skeletons. So it's not like living things skeletons, as you see here. We have heart, we have pyramidal something, etc. We have 1,725 images in 90 categories, and the challenge is set up as 70% training, 15% testing, and 50% validation subsets. Then we have point skeleton, point skeleton, and I'm really apologizing about my allergies. I can hear my voice deteriorating over time. I'm really sorry. So for point skeleton, we have 1,725 point clouds in 90 categories. Again, this is very similar to what you have seen in the pixel skeleton. Extracting boundaries as 2D point clouds, and the inside is filled with different grid points and then sampled and perturbed differently. We also provide the sampling scripts and noise distribution scripts so that if you want to try the different point clouds, you can also do that. the skeletons are close enough points to the points that are close enough to the original skeleton are output as labels, and these are either can be separate point clouds or labels on the existing point cloud points. Then we have the parametric skeleton. Here we have the shapes as images as the first one, and skeletons are represented by degree 5 Bezier curves. The control points of the Bezier curves are given by X, Y, R. And again, same number of shapes, same number of categories, same splits. And the parametric ground truth data includes the file for ordered control points. For the ordering of the branches, there is a special algorithm called WEDF that I unfortunately don't remember what it stands for, but it is actually ordering the branches based on being the main branch, then being the secondary main branch, then etc. So it splits if continuous, merges if equal, and maximal weighted function along a branch, basically. Last one, the image skeleton. Now we are expanding to in the wild images, right? Like now we need more and more data than 1,700 images. So we have 52,215 images, and skeletons are labeled as pixel, like pixel-wise labeled. They are natural images in 17 categories. And these are all diverse categories, as you can see in the images on the background. Now, how do we evaluate the results? So for pixel and image skeleton, we are looking at the average F1 score. For point clouds, we are looking at the chamfer distance. And for parametric skeleton, we are looking at branch ordering and control points. So the MBE actually looks at whether the order of the branches are similar, and MSD looks at whether the control points are actually similar to the original control points in the ground truth. So then we weight them. For results and baselines, there is for pixel skeleton. This is like the baseline is old, so we use the vanilla pix to pix, and we apply it after distance transform to pre-process. So you first get that distance transform in B, and then you apply it, so you can get the result in C, and D is the ground truth, if I remember correctly, or vice versa. I think, yeah, B is the ground truth, C is the baseline. It gives us an F1 score of 0.62. For point clouds, the ground truth skeletons are used as labels, so this is more of a point-wise classification task than a shape transformation task in its form. We want to classify each pixel, but of course this gives us an imbalanced class, right? So the skeleton will always be n square, n, and the total image or total point cloud will always be n squared. So we use a PointNet plus segmentation module, which is adjusted by dynamic weight, and it gives us a mean IO of 0.59. Then for parametric skeleton, we have modified resonance that can actually extract these. Then regression of binary images to 6 control points as X, Y, R. This again depends on the shape complexity, but the ground truth is limited to 5, so we also limit to 5. And the connectivity also matters. So as you see here, like some branches may be found as important and exported as the one of the 5 branches, but the connectivity may not be preserved in those like top 5 branches sometimes. And the pixel loss is given there when the shape is regenerated from those parameters. And for images, we said coming soon because we did not publish these results. But if you go to the leaderboard, I think we have some baselines submitted there. And you can see the baseline images from the image skeleton here. These are the references of the data set, of the skeleton extraction that we used, and on the original skeleton paper with the 3 challenges. If you want to go play with them, we have them here. Bitly, skeleton, pixel point, param, obj. Those are the different 4 different challenges. Sorry. We also want to, as I asked to the previous presenter, we want to actually expand our challenges with expand the skeleton challenges with new tracks. So one idea that we had last year that we didn't have the data prepared in time this year for this year's challenges was, can we actually do topological shape understanding, or can we find the genus of the shape by just deep learning instead of like shape, or in addition to traditional shape approaches or shape understanding approaches. So with that, maybe it is actually a good time to smoothly transition to the collaboration session, because we are already a little bit late on time, right? Should we go into the, yeah, okay. So let's actually start the collaboration session. Oh, sorry. Uh-oh. I'm sharing, don't worry. Okay, are we back? Hopefully. Okay, cool. So now you know the skeleton challenges, now you know our workshop, you have seen the topics in our workshop. I think we can go through these questions, or if you have some ideas, you can just throw them. And this is basically a practice to find people with different perspectives working on same problems. What basically, like, what intrigued your interest in this workshop, or what are the current gaps that we can fill with our collaboration? Or we can even just like start by introducing who are you, why are you here, and what are you currently working on. And I know that as curious researchers, we all have something to say when we hear about a research topic. So with that, I want to open the floor for any of the topics that you see here and you want to talk about. So last year and previous years, how we do this was like a family gathering, like everyone can contribute and talk about. You don't even need the microphone sometimes. What we did was for the Zoom participants to also hear it properly. I was repeating the questions through the microphone, or repeating the comments through the microphone, while people in the room were talking between them. Your moderation to that would be you speaking to the microphone, but that's also fine. For the Zoom participants, I will just, I want to get the chat into this window so I see it. Just a second. I'm looking at which one.
You want to have the chat here?
Yes.
Okay, that's. Here you go.
Yay. Okay, awesome. Maybe the first one is an easier question. I can just ask that and you can maybe answer quickly. What would you like to work on if you can pick one topic from this workshop? And it doesn't need to be exactly one of the things that we talked about. It can be tangential. It can be in the general area of the workshop. And I also see the chat right now. So if the Zoom participants wants to answer, I can also see and read them.
That everybody who wants to contribute come a little bit forward and the content to scream at each other.
Come closer. Backseat people. We don't fight. I don't. Yes.
Yeah, just had a question about, it's not really one of these because I wasn't there for the rest of the workshop, so but can you give us an overview of what skeletons are used for? Like, what are the applications? Because I've seen them like, as intermediate steps for shape understanding in some methods. But like, I'd be interested in knowing exactly, if you have like a list of the areas where we use skeletons.
Well, shape understanding have been used in many different domains. If you look from the very, very top, you can even see like computer graphics, computer vision, machine learning, all of those domains using. And in the application domains, as Bernard said, like one of them was like medical image domain, because there's so much like shape understanding in that one, related to different organs, related to different diseases, like some specific shapes representing some specific biological factors. The other one is robotics. I think someone said in the robotics world, you said that, right? I don't remember. Someone said that in the robotics world, someone was using. So in that case, like not specifically object understanding, but for interaction understanding, for hand pose, for placement, etc. The shape understanding is actually very important. And of course, like most of the categorization tasks, right? Like labeling, like segmentation, like human pose estimation, all of these have intrinsic shape priors in them so that they can actually be used. And of course, like all the analysis tasks that we have talked about have the complementary synthesis tasks. So how can we embed shape priors into generative models? How can we create specific shapes, specific categories, specific labels with objects with specific features using those shape priors, etc. is also another topic. So these are all application areas of shape understanding, I would say.
Okay. And specifically about skeletons, because you talked about shape understanding, but are skeletons used in all these domains, or is it?
Let's think. Medical domain, yes. Robotics, probably. I'm not a robotics person, but I guess I saw some, at least for like hand pose estimation and hand object interaction. Let's see. For graphics, obviously, right, there's so much collision, etc. And for animation, for rigging, all of them uses skeletons. For content creation, probably, like anytime we are putting things in an environment, we don't want them to collide. So probably that's actually that's actually used too. Yeah, I guess skeletons are no different than general shape understanding in terms of applications.
Okay, thank you.
Yeah.
I actually got another question about the skeletonization, sort of the Bézier curve one. I was curious what the logic was behind using the control points as kind of the metric of success rather than like an arc length parameterization or something. Like, is there something fundamental about like having the parameterization domain be the important part there for the usage of Bézier skeletons?
That's a good question. I want to ask if either Catherine or Geraldine is on the call, that they can actually be much more helpful for this question. They are not. Oh. They are the main person, the main maybe responsible for the parametric skeleton, but I think that was in terms of like control points are also a parameter, right? So maybe that was representative enough in their formulation that was good to use. Otherwise, how would you compactly represent the Bézier curve? I don't know. Like there may be other curves that we could have used, like other parameterization of the skeleton. That
no, I don't know. I mean, just for evaluation, like you have two curves that look very similar in like the arc length domain, but have different control points that are far away from each other because like the speed at which you move on the curve is very different. So I'm kind of curious, like I just didn't know in this domain, like is how the speed of parameterization would be important to applications, and that's like something we care about. Is it, like,
that's a really good question, and I think we should also think about how if it is creating any ambiguity, you know, in terms of our evaluations for parametric skeleton, yeah, definitely. Let's talk it with like Geraldine and Catherine. I'm sorry, I wasn't as helpful. By the way, I don't want this to be like a questions to Inke session. This is like everyone collaborating all together. Okay, I will start with the question to this gentleman here. Who are you? Why are you here? And what are you currently working on?
I will answer a different question. No, I thought, yes, so I'm Bernhard Ecker. I'm a junior professor at FAU in Germany. It's the best university I've never heard of. And I work on 3D computer vision with generative models, shape analysis, mainly with PCA, so very old school correspondence-based shape analysis, for faces in particular, but also for body shapes. And I also have some research directions more into the direction of trying to understand how human vision works. And that's also very often that comes together. So that's the answer to your questions, I think. And what I want to bring up is what I thought was pretty interesting when Pavan presented before, is that the people that are now here are all the people that asked questions before. And your last question here is, no, the second last one, no. There was a question, it's like from all the topics from the workshop, which one would you?
The first one.
The first one, okay. Not the last question. So for me personally, what you presented before was the most exciting one. And I had a project that was somewhat related on it already. But I think there is a lot of things that can be done on top of what you have done. Perhaps a lot on the application side, like you show that it works and you show feature visualizations and everything. So it's kind of low hanging to just exploit that. And I already mentioned it before, tried out medical data. And that's where the answer to your question becomes important, like what am I doing and why am I here? As a tutor, that's where I have students that look for projects. And in a lot of those student projects, it's pretty cool to aim at that low-hanging stuff where they can take something that kind of works and apply it to something new, to learn things. And if everything goes very well, which is, as you probably know, super unlikely with student projects, and then it's also potentially being publishable at, like perhaps not at the top conference, but for example, student projects are sometimes nice for workshops or second-year conferences or local things. So that's from all the topics of the workshop. That was for me that I don't know if that's the same for you. I think some of you came for the last presentation. You want me random? Yeah, well, I mean, I do currently here. Yes. It's probably cool stuff going on here. Yeah, getting blood. Yeah. What about you? I used to look at that. Yeah. Did you see the first presentation? Yeah. Did you see the I don't remember what conference it was. There was a keynote by Lisa Braunstein 1 year ago when he was still at Twitter, about geometric deep learning, graph neural networks, something. And it was ICML, I think. Yeah, you're right. And it was, if you haven't seen that, you definitely have to watch it. It's like the best Hollywood style keynote I've ever seen. And Michael Branch. I think it's all the research about the airline program of geometry, which is called is FAU is in airline, and that's where the airline program is coming from.
Basically, focus on how we can shape information.
So there is a poster tomorrow morning, the first session, the shading modeling approach to using logical estimation. There are a lot of them actually. It's CVPR. The one tomorrow morning is by one of the students, and it's one of the highlights. So there we go there. It's called clicks. So yeah. What brings you here?
Yeah, did a lot of geometry. I guess the most recent work I did was on suture needle cut. People are a lot. It's on suture. So it's a semi-critical suture, so it's semi-critical. And it has a lot of really nice geometric problems. It ended up being the best paper at ICRA, just
Woohoo!
so it's yeah, it's great. Well, that's medical, but yeah, and it does all the. It's really primitive actually. It's full projection, and multi-camera model, that sort of stuff. So I'm very interested in a little bit of lines, simple geometric curves.
And you're here to present your work.
I mean, thank you so much for first of all accepting our paper. You know, of course, I'm here to present, but you know, we had a similarly themed workshop series, which during the COVID years, I'm forgetting when we stopped it, but I think roughly ran from 2016 to 2020. It used to be called Differential Geometry in Computer Vision and Machine Learning, DIFF-CVML. And we struggled with finding a community that was engaged, and it was because of I was the only engineer on that workshop organizing team, and the rest were mathematicians and statisticians. So they have a very specific way in which they talk about shape, and the contemporary conversation there is infinite dimensional shape spaces, you know, the spaces of diffeomorphisms and continuous curvature shapes and stuff like that, which is nice math, but I always struggle with making it real. But there is a pretty large community out there who studies increasingly more sophisticated methods for shape analysis. And they would consider this stuff to be super basic, but they are there. So when I saw this, I mean, I did not track DLGC over the years. I just thought, okay, this is done and geometry is over. But this year we found DLGC, and then I saw it was running for the last 5 years. So I feel like there may be a good reason to try and get some of those mathematicians in, but maybe not all of them in. Not discrete. Make it discrete at some point, but there's who are these people? Oh yeah, those would be the more practical graphics types of people, right? So these are people like the ones I have in mind are people like Michael Miller from Johns Hopkins, you know, Songshun Zhu from UCLA. So these are people who descended from the 1980s shape community, which really very quickly went into continuous shape spaces. So for them, a shape is not a discrete set of pixels, it's a continuous curve. And then how do you describe that? Super complicated math and that sort of stuff. Right.
I work at leadership center, mashing together research values.
Yeah, but then the Justin Solomons and you know that set of people, they also have their Summer Geometry Institute. Have you?
Yes.
Yeah.
One of the mentors this year.
Wonderful. I was laughing. So I was a mentor 2 years ago, but I gave up. You know, it's so hard to be, you know, summer mentoring. So yeah, maybe there's a way to bring it all together and make it a real big thing.
Yeah. I've seen a lot of attempts in the shape modeling area. The first attempt that I've seen was the Shape Symposium in Switzerland, which was a very local conference like thing, which was a separate event. And I still have collaborated in that thing. It died after times being organized. And then at Nikai, there's a workshop called Shape Me, which I organized once or twice. which is happening this year. So if you take a paper somewhere, I think the deadline is in July. At Mika, there are also 2 workshops that are in the shape direction. They were usually alternating. Now they are in the same year. The other one is more on the mathematical side. So there are several attempts, but I feel like each one of those attempts feels like it's not the same what the other attempt is doing.
Right, right,
and,
right.
I think that's a kind of a barrier, or I don't know if it's a barrier, but I also don't know what the problem is.
I mean, I think people talk about SHIP in very specific ways in these different communities, and I think they see each other as competitors. That's the problem.
Yes.
Yeah.
It's also work to organize and stuff.
Right.
I've seen a lot of those attempts that we stopped after 2 or 3 iterations, or had some breaks in between or whatever, and most of that was because the person who organized was not a postdoc anymore, or went to A3, or got the faculty job started or whatever. So like bringing those different events together might save a lot of time and might be much.
Right, but I think to that point, to bring it all together and make it one coherent event has to be at the level of a whole conference, right? I mean, otherwise.
Yes,
yeah,
right. So people don't want to travel just for a virtual event.
Right.
He's not around the world.
Right.
So that's the first problem. If you want to catch people at CVPR, you have to bring it to CVPR.
Right.
We were one of those 5 years we were at ICSP. So it's really for virtual, it's hard to get people to travel. That Shapes Symposium was organized in the middle of nowhere, that funding reasons, because that particular state in Switzerland provided funding is in the middle of nowhere. So we visit in the middle of nowhere and try to convince people to travel to the middle of nowhere for something where you don't get a foundation out of it especially in our fields, like also in UK, there are publications like on the other side, really comfortable traveling around the world and go away without publications for an abstract.
So talking about communities, we still have 4 people online. Are you able to hear us and see the conversation well enough? I'm just trying to use my phone as a camera to show the room. So can someone tell me that this is useful or not useful, or are you feeling enough to be a part of the conversation?
The camera is great. Thank you for just showing that, but the voice is not very clear from the audience.
Got it. Okay, we can actually repeat them when they talk and you don't hear.
Yeah.
When we use the microphone, you can hear us, right?
Yeah. With the microphone is very well.
Can I just quickly ask, you're both PhD students, postdocs? PhD students, almost finishing or starting? Almost finishing. Yeah, both starting. Yeah. And where are you from? Yeah. That's somewhere close here, right? Okay. So we have one from University of Washington, a PhD student almost finishing, and one from British Columbia. And who do we have online? It's Dana, right? You're still awake?
I'm here.
You sleep?
Actually, we can put them here.
So Dana is I don't know what professor, associate, or lecturer, or what is the actual, you're a professor in the UK, right? At Plymouth.
Yeah, assistant professor.
Assistant professor, okay. And then there are John, Huang, Yong, and I don't know how to pronounce that name. Are you still awake? Are you with us? Do you want to talk with us? No? Okay.
I think Thierry is also there. You don't see the chat. I see the chat. Thierry said that, and sorry if I'm mispronouncing your name. I can see that the audio is low. We are trying to talk to the microphone, and they are here.
So one thing I still would like to hear from all of you actually is what was the most interesting thing for you? First, from some of us, you've heard it. And for you, you can't say your own what was the most interesting. So what would you say?
I really like the question we want to talk about. I really like education a lot.
Yes.
Because for starting, applied aesthetic, computing, and the divisions that
He's saying that TED Talk was the best.
I mean, here is a lot of gap. But on the 3D side of things, there's not one of the gap.
And on the 3D side of things, there's the gap between engineers and artists and mathematicians.
I really like that. Especially with like VR and it's like worlds taking off.
Virtual worlds and VR taking off. We need more detailed ways to tackle that.
Yep. Speak to the people who do these reports, they say, it's like, yeah, the things that do the person that not complex come to the world. And I will drop that question out. It's not always about photorealism. It's something else.
It's not always about photorealism, but it's something else.
That's something that came also up before when you were talking about the challenge, and you brought up like, why are you using this method of that one? And I was yesterday at a workshop about generative models, and there the very first presentation was like, we have this problem, we have this problem, and we have that problem. The last problem was evaluation. And then the whole day people were talking about how they solve the first and second problem. Nobody's talking about evaluation. And I think that that's for me almost a common scheme in almost everything. It's super hard to evaluate what you're doing, especially practical usage of it. And there's probably way too little work on how to evaluate stuff probably. And I think that slowly becomes to be one of the lowest hanging things in the community. Just be the one person or the one group that really tries to work on how to come up with live evaluation. Because there is no way that all those massive developments we have from the last 10 years are not useful for evaluation.
Yep.
Then also this, Syria is suffered every time someone came up with a management.
Yeah, so we just have to make a metric that's harder to tune to. Like the more general your metric is, the harder it will be to tune it for that metric, and it doesn't generalize to other metrics. And yeah,
what you have like aesthetic almost yes,
our metrics involving people better.
I mean they evolve over time. Just
Yeah, that's also something that we work on in my group. Like, what are more human metrics? This can be metrics that measure trust. This can be metrics that measure artistic expressivity or creativity. And trying to put only technical, completely numerical metrics on this is hard, but why not doable if we have enough data? Can we actually measure those? So that's something we are also working on, and I think that has that should have some reflections in the shape domain, like symmetry or aesthetics or ratios, or like all of those are. This is me talking, sorry. I was like showing you guys. All of those are like can be somehow maybe represented in an artistic evaluation metric. I don't know. That's something I also we are working on. Now that I'm talking, I want to ask one more question. I know I mentioned 2 times before. This is the third time. Anyone is interested, anyone here or anyone in the Zoom interested in the next iteration of Skeleton challenges? This can be a completely different shape-related track. It can be an improvement over one of the existing tracks in a different domain. It can be, as I said, like some expansion to topological processing. Or it can even be, we need some technical help because the current organizers are running out of time doing everything. And we also need some hands carrying the challenges over other domains, over other frameworks, sorry. So is anyone interested in that? Okay, I will be waiting. I'm taking your word.
Nice video, by the way.
Yeah, really? What time is it?
Should we do the closing and then we just go to the conference center and see if there's left or something or call? Should we do that?
We have 5 minutes left, no?
Yeah, but for close, like the.
That-
We can also continue.
No, I think this is good. There's no closing remarks. Like this is like thanking everyone. We have one thing and that's it. Yes, yes. No, I'm saying that we don't have that elaborate 15-minute presentation. That's what I was saying.
Don't have to elaborate.
Yes, okay. Okay, we have one thing to do, and I'm glad that the people that are related with that last thing are here. So let me.
I think I need to switch slides.
Yeah, I know, but I need to take this first. Sorry, Dana, you are coming off camera. Okay. Okay, last thing that we need to do, and Bernard is doing this. Da-da-da-da.
Yes, so, wait, we go one slide back. No, yeah, so, you have to listen now, we have in the board, it's the best paper award. And, the best paper award is solely based on the reviews by our program committee. So what we did is we did take the ratings from the reviewers, we averaged them, and we give the best paper award to the paper that scored highest. Okay, that's the procedure. So it's not based on anything that happened today. It would probably also get the best presentation or the most interaction award we had. So it obviously goes to you. We also have to apologize. There is no price to attach to it. So we this year didn't get funding from the industry. But you get this very nice prize, and I think we should take a picture.
Let's take a picture with that.
With the prize.
Can you take the picture? Yes. But it was a really nice presentation. You definitely deserve it. And that's here.
We are taking a photo in front of the slide, that's why you don't hear us.
Thank you. Bring it to your student. And you can send it.
Yes, thank you. So, wanna close?
Yeah. Yes. Yeah.
So thank you everyone for coming. I know we are just closing. Thanks everyone still staying in the Zoom. Thanks everyone in the room. And I hope to see you, all of you, in the next version of the RGC in Deep Learning for Geometric Computing workshop. I just want to put this, sorry. Whoop. Sorry. Okay.
Thank you. Thank you, everyone, also.
Yes. I want to thank Dana.
Thank you for you being there.
No, sorry, that people are talking. So one last minute, I want to thank Dana. She's the main. Can I have attention for a minute?
Don't worry. That's fine.
Sorry, 1 minute, just 1 minute. Yes, sorry, thank you.
Yeah, don't worry.
Organizer Dana, who is on the call, and it is so great for her that she's still here listening to our talks, and one last applause for her.
Thank you.
She keeps all of us intact, not going like headless chickens. Thank you, Dana, for doing everything that you are doing.
Thank you for being there.
Absolutely. And hopefully we will see all of you next year in the 6th version.
Yeah. Bye.
Okay, thank you.
Good night.
Good night.
What time is
Bye.
it? Like in the morning?
Sorry,
What time is it now in the UK?
1 o'clock.
Well, yeah, you survived.
Yeah. Okay. Okay, I close this. I think you are there, so I just close this. Yeah.
Bye bye.
Bye. Thank you for everything. Bye bye.